of us learned relativity from. And he says the real reason for our adherence to this principle is not that it is surely correct, but that it allows us to make use of the limited data which is available. And he also says that if the data will not fit into this framework, then, well, we have to go back to square one. And that is precisely the topic of my talk today. Now, meanwhile, of course, we have made a huge amount of progress in cosmology, observationally, but the framework we are using to interpret the data still goes back to this 1921 paper by Alexander Friedman 100 years ago. And that is based on this idea that the universe can be described statistically as isotropic and homogeneous. And we all know that that assumption is crucial in the inference that the universe is today dominated by cosmological constant, sometimes called dark energy, and that the scale of this constant is in fact the present day Hubble parameter. Not quite naturally, because that is the only scale with dimensions in the Friedman-Robertson-Walker metric. And that scale today has a value of something like 10 to the minus 42 GeV, an infrared scale, not a scale in fundamental physics. And of course, it also varies with time. So I find it very bizarre that this should be now considered to be some fundamental property of nature, because I can't see that it can ever be so. And I'm inclined to believe that this is because we are interpreting data in a constrained framework where this is the only scale that lambda can take. Now, even though it makes no sense physically, the enormous effort that has been made in observational cosmology over the past few decades has focused on measuring the parameters of this model to increasing precision, but not to check its foundational principles. Now, the first thing to observe is that the universe is in fact not isotropic around us, because we see this dipole in the cosmic microwave background, which was in fact predicted in a precise paper by Dennis Sharma in 1967, because he already knew that we have a peculiar velocity with respect to nearby galaxies, and that should induce a dipole. And soon afterwards, this dipole was in fact observed, and its temperature across the sky, as you know, agrees with what you expect for an observer traveling with respect to the frame in which the CMB is truly isotropic at a speed of about 1,000th of the speed of light. Now, this is a figure from George Smoot's Nobel lecture, where he illustrates the various velocities that go into this problem. So we happen to be moving around the galaxy. The entire solar system is orbiting nearly opposite to the direction of the CMB dipole. So these two velocities add up more or less. And our net motion of the local group, that's including Andromeda, Large Magellanic Cloud, etc., is almost twice. It's 620 kilometers per second, roughly towards the Shapley supercluster. And the idea is that, of course, the universe is inhomogeneous on small scales, but it should become homogeneous when averaged on scales larger than about 100 megaparsec. And then we should so-called converge to the frame in which the CMB looks isotropic. We can apply our standard Friedman-Lemaitre-Robertson-Walker equations and do what we do. But we first must find evidence that we are in fact going to converge to that frame. Meanwhile, all data is already corrected by transforming to this hypothetical frame, simply because this, as I said, this dipole in the CMB was predicted and then observed, and it agrees pretty well with this kinematic interpretation. Unfortunately, this convergence to the CMB frame has not been seen after decades of effort, making some rather difficult measurements of peculiar velocities, for which, of course, you need independent distance indicators, and that is the rub. However, a series of measurements using various catalogs have tried to infer our peculiar velocity, which ought to fall off as 1 over r as we average on scales of r. But we find that compared to the expectation from the standard lambda CDM model for structure formation, there is a consistently higher value found for the peculiar flow. Now, these measurements are somewhat debated. There is controversy about some of them, and I understand Mike Hudson may speak later in this symposium. He will give an outline of those. However, we can already infer the following, that we are not Copernican observers, because we are not, a typical observer would not see such a high flow as we do, stretching out as deep as we see to go. And we have quantified this by interrogating the largest lambda CDM simulations done, called dark sky, and we find less than 1% of observers such as us should see such a bulk flow. This is important to keep in mind because this has a direct implication for the covariances that are normally employed in analyzing, for example, supernova data. But let me come to the main topic, which is that if I open a good textbook, say Jim Peebles' book, he shows this picture of radio sources mapped from Green Bank, and he says this illustrates the anisotropy of the universe. I looked at this picture a long time. In fact, I wondered what that little line there was. That's actually the Milky Way up there. These gaps in the picture are regions that you can't see from Green Bank. But on top of that, we have this little dots representing the position of radio sources at 6 centimeters, and they are supposedly isotropic. That's what people say. Actually, that is not correct, because if we are in fact moving with respect to the frame in which the universe looks isotropic, then the distribution of distant sources should also be anisotropic, should also have a dipole, just as the CMB does. And you can't see that in this picture because these are only about 30,000 radio sources. The effect would be of order V over C, so you need to have more objects. And the fact that this consistency check could be done using a catalog of distant sources was first appreciated by George Ellis, and who you all know, and John Baldwin. He's a radio astronomer at the Cavendish Lab. They pointed out that the classic effects of aberration and Doppler boosting should create a dipole in the sky for a flux-limited catalog of objects. Now, aberration, of course, goes back to 18th century. Bradley discovered aberration when he was, in fact, trying to measure parallax. This is a much bigger effect. It's due to our local motion, and it basically squeezes objects in the sky towards the direction of our motion. And you have to take account of the fact that if they have a, say, power law spectrum, then you're sampling a different part of the spectrum as a moving observer. And therefore, when you look at the number of objects per unit area on the sky, if you know how the flux distribution behaves and how the spectrum behaves, those exponents are what enter into this expectation for the dipole, which is, as I said, always going to be of order V over C. But this number can be of order few. Now, this test would appear to be the thing to do, but already Ellis and Baldwin estimated that you need a few 100,000 sources to do this. I find it quite amusing that they wrote this paper at the Orthodox Academy of Crete, where George tells me there was a cosmology conference in 1983, and that's where they met and did this. And they were very clear about the significance of this test, that if the standards of rest determined by the microwave background and the number counts were to be in serious disagreement, one would have to abandon one of the assumptions that go into this. For example, the sources may not be cosmologically distant. One of them might be close by and give a anomalous dipole because of that. Or the CMB may not be relic radiation. I don't think anybody today would believe that. The third possibility is that we must question the standard Friedman, Lemaitre, Robertson-Walker models. So I think that is pretty powerful motivation to conduct this test. And yet, as I said, very little attention has been paid to this until quite recently. Now, if you look at the all-sky catalog of sources with some redshift distribution, ideally you would want them to be at high redshift, beyond 1, because you don't want a so-called clustering dipole, which might result from the fact that one or more of the sources happens to be accidentally very close to us within a few hundred megaparsecs. And that, of course, would create an artificial dipole. But this clustering dipole is irrelevant if you have sources at high redshifts. And this kinematical dipole, which is what you're looking for, is independent of the source distance. It just depends on our velocity and the spectrum and flux distribution. And obviously, you need a lot of sources to make sure that the short noise is under control. Now, I will report on 3 catalogs you have examined for this. One was a catalog of radio sources, combining the radio catalog made from the Very Large Array, New Mexico, with a catalog made from Molonglo in Australia. And we analyzed that now 4 years ago. And we found that there was an anomalous dipole in that. We believe the clustering dipole in that is negligible, but it's estimated because you don't actually know the redshifts of the sources. Then we looked at a lot more galaxies from the WISE infrared satellite. And again, we found an anomalously large dipole. But these objects have a redshift which is not so large, and therefore clustering dipole could be important. Our final test is with the same WISE satellite, but a catalog of quasars. And these do have redshifts which are high, and we have spectroscopic measurements to prove that that is the case. And therefore, we can neglect any clustering dipole in this. Now, sorry, I should mention that all this work is done with Jacques Collin and Roya Mohai, my collaborators at the Institute for Astrophysics in Paris, and Mohammad Ramiz at the Tata Institute in India. And for the last paper, we are joined by Nathan Seacrest, who is at the Naval Observatory in Washington, and Sebastian von Hausegger, who is at Oxford with me. Now, this radio catalog that we looked at, we tried to create an all-sky catalog by combining these two and scaling them appropriately to match the source density in the overlapping region. And then you make various cuts to make sure that you don't have a false clustering dipole from nearby sources, especially by cross-correlating with the 2MRS infrared satellite catalog of objects, which is not affected by extinction, as you know. That's why infrared is so good. And when we did that, we did find the expected dipole, the familiar cos theta pattern. You can see it visually on the sky. But the problem is that the corresponding velocity is much larger than what you infer from the CMB. And this had already been noted by Ashok Singhal some years earlier. But he did not have the full sky. He just looked at the NVSS catalog. And although we are getting on close to a few 100,000 objects, the significance of this measurement is not really that high. We estimated that by Monte Carlo, and we found that it's only 2.8 sigma. There is still about 0.25% chance that this is just statistical fluctuation. Also, these radio source redshifts are not directly measured. You estimate them from the luminosity function. Now, the next assessment we did was for the optical galaxies, sorry, the infrared galaxies mapped by WISE. In fact, it has mapped like, several 100 million objects, but most of those are stars. And Ramiz, in fact, found a smart way to remove all the stars by simply looking for apparent motion, because the satellite functioned for several years. And you can actually see the stars moving when you look at the pictures taken at different times. And when we do all that, we are able to isolate the galaxies as opposed to the stars. We still got over 1 million galaxies. And again, we find an anomalously large dipole. The statistical significance is now much higher. However, because the redshifts are very close to us, the clustering dipole can be significant, and we estimate that it is not high enough to match what we observe. So either way, there is an issue. Either the clustering dipole is anomalously high or the kinematical dipole is anomalously high. But because this was not so clean in the sense that the objects are close to us, we figured we need to do better than this. And that is something we have been able to do quite recently. using the cat-wise quasar catalog that was put together by Nathan Seacrest and collaborators. And this, after various quality cuts and much checks for systematics, etc., comes to about 1.4 million quasars. And the big development is that part of that sky was mapped by SDSS, and EBOS has measured the redshifts of about 10,000 of our quasars. And they are definitely at high redshift. These are spectroscopic redshifts, not photometric. And so we can say with some definiteness that 99% of our quasars are at a redshift higher than the point at which they would give you a clustering redshift, clustering dipole. You can see the dipole on the sky in these quasars, and we have to now compare it with the expectation from Ellis and Baldwin. And for that, we do something a little more sophisticated than has been done before. We have the distributions of the spectral indices and the fluxes. We sample these and generate Monte Carlo simulations. We run 10 million such simulations, taking pairs of these such that overall we represent the underlying distributions accurately. And when we do that, we find that the quasar dipole is consistent in direction with the CMB dipole, which is marked as the star up here. And here is the quasar dipole, about 28 degrees off, but within uncertainty is consistent. However, if you look at the amplitude of the dipole, this vertical line, dotted line here is the expectation from the kinematic hypothesis. This distribution is what our 10 million Monte Carlos give us, taking into account all uncertainties. But what we observe in the sky is very far away from that. Indeed, only about 5 of those 10 million simulations could get up to here. So very transparently, the statistics tell us that the p-value is 5 times 10 to the minus 7. For a one-sided Gaussian, that's 4.9 sigma. Nathan will perhaps give more details about this in his talk on Friday. And I just want to say, I invite you all, if you have any concerns about this test, to look at our data and code, which we have made available on this website. And we believe in open science. Everyone should check us. Now, let me take a few minutes now to tell you what the implications of this are. As I mentioned, it is routine practice to boost to the CMB frame, or the cosmic rest frame, better called, in which the universe supposedly looks like a Friedmann, Lemaitre, Robertson, Walker universe. And so all redshifts are routinely transformed to the CMB frame using standard special relativity. And on top of this, peculiar velocity corrections are applied to objects which are close to us because they are in this bulk flow that I mentioned earlier. And when we looked at the largest catalog of supernovae for which this had been done in a manner that we can study, because they had kindly made their entire catalog, all covariances public, we found that the peculiar velocity corrections that they had applied, which are, as you can see from this formula in this figure, all to do with special relativity, right? These are the standard boost corrections. The corrections, as you see here, stop dead at about 150 over h megaparsecs, right? In other words, these authors had assumed that by that point we converge to the CMB frame and the universe looks isotropic. However, I showed you data earlier that indicates that this is not the case. They were too optimistic in believing that we have already achieved the CMB frame. So we undid the corrections to get at the raw measurements that made in the heliocentric frame. And then we would like to ask if in that frame, how does the universe look? How does the expansion behave? And what we found, to our surprise, actually not entirely surprised, I'll mention this, if we do a cosmographic expansion of the luminosity distances of the supernovae, which does not assume any dynamical model, but it does, of course, assume FLRW intrinsically. But we then tweak it by allowing the deceleration parameter, Q0, to have both a monopole and a dipole component. Now, this is not totally consistent. Ideally, you should analyze the data starting from a anisotropic flow metric. But, with only 740 data points, there is only so much you can do. But this is already very interesting because we use a maximum likelihood estimator, which we had shown earlier is the correct thing to use for this kind of data. And we find that the MLE then picks out this deceleration parameter, which is, of course, as we know, an acceleration parameter, that it is in fact largely a dipole, and the dipole is about 50 times bigger than the monopole, which is on the x-axis. The y-axis has been compressed by a factor of 10 in order to put on the same scale. And you observe that the monopole is almost consistent with 0, the vertical line. It's only significant at 1.4 sigma, whereas the standard lambda CDM model, which has got 0 dipole and a large monopole, is rejected at nearly 4 sigma. And this suggests that this acceleration that we have inferred is really an artifact of our being located in a very deep bulk flow. And the motivation for this had been given to us by the work of Christos Sarkar, who will also speak later in this conference, who had noted that a so-called tilted observer who is in a flow would see this sort of anisotropy, which would be aligned with the direction of the flow. And indeed, this dipole is aligned with the direction of the bulk flow. Of course, we cannot establish this very precisely, again, because there are only 740 supernovae, but it is consistent. And the interesting remark one could make is that the two collaborations that first measured the expansion of the universe to be accelerating were mainly looking in this direction, as you can see from here. So if you average over the whole sky, you will find that the expansion is consistent with being at a constant rate, as we had shown in an earlier 2016 paper. But if you look in only one part of the sky, you might see acceleration or you might see deceleration, depending on what direction you're looking at. Now, let me very quickly say that our finding was criticized, and I just want to make a point that Rubin and Heitloff redid our analysis and they recovered what we find. This is a plot of the dipole versus the monopole, and they recovered this pink patch, which is what we found. But then they criticized us, saying that we should have allowed for the light curve parameters to be redshift dependent. We didn't do that because it doubles the number of parameters. We don't think it is statistically justified. But if you do that, then you increase the monopole strength, you go to this green patch, but you don't actually change the dipole. It stays about the same. Then they say we should move to the CMB frame rather than use heliocentric redshifts. Now that will just flip the sign of the dipole for the reason I gave you earlier. We are moving around the galaxy in the opposite direction to the CMB. So that doesn't solve the problem either. You still have a large positive dipole and a small monopole. Then they make peculiar velocity corrections that we had questioned, and then you get to the quote right answer, which is this gray patch here, consistent with 0 dipole and some monopole. But that monopole is only significant at, I don't know, 3 point something sigma. And this assumes that the CMB frame is the correct frame, which is what we are now questioning. So prima facie, the cosmic acceleration, which we inferred from supernovae, is anisotropic, and therefore it cannot be due to a cosmological constant. So let me conclude. The standard model of cosmology was established long before we had any data. And now that we have data, we ought to be testing its empirical foundations, as was done, for example, for the standard model of particle physics. Similarly, every aspect of its assumptions has been tested down to the quantum level. Now, we observed that there is a dipole in the recession velocities of the host galaxies of supernovae. That was in the bulk flow diagram I showed you. And this appears to be stretching out beyond the point at which the universe is supposed to become homogeneous, according to galaxy counts and all that. And we believe that the inference that the expansion is accelerating may just be an artifact of this. Even more importantly, we now believe that the rest frame in which distant quasars are isotropic does not coincide with the rest frame in which the CMB is isotropic. Now, this is rather profound. This is a real body blow to the fundamental structure of the Friedman, Lemaitre, Robertson, Walker models. This, therefore, needs to be checked and double-checked and done with independent catalogs and verified by independent groups. But if it stands up, then this casts doubt on the framework itself. If that is the case, then I believe we must start again to reconstruct a new standard model of cosmology. And the manifesto for that was given by George Ellis and collaborators some years ago. This is the so-called cosmological fitting problem, in which they outlined all the challenges that are associated with doing so. Let me finish by showing you a slide which reflects the position of one of the pioneers of cosmology. You all know of Vera Rubin. Many people believe she should have got the Nobel Prize for discovering dark matter, etc. Fewer people know about her pioneering work in measuring peculiar velocities and the bulk flow of the local group. And in an interview where Alan Lightman asked her, how has finding that the universe is more inhomogeneous than you would have thought altered your view of the Big Bang model? And I was really amazed to find that Vera Rubin had said very categorically that she is not sure that the Robertson-Walker universe exists. And this was in 1989. This is, 22 years ago. She was very much ahead of her time in questioning the assumptions that have led to our standard model of cosmology today. Thank you very much.
Yeah, thank you, Subir. And thank you for sparing time for Q&A. Any questions?
Thank you.
From the audience? From participant, yes, please unmute your speaker and just ask a question.
Thank you, Professor Subir. I am Pavan. I have a question regarding the last statement you made, like the rest frame of the quasar being not equal to the rest frame of CMB. Is that you meant in the terms of magnitude, or also including because within the reverse, the direction is essentially consistent, except for the acceleration being different. I mean,
that's correct.
Amplitude being different. So, what does that statement essentially mean? I mean, precisely mean?
Well, the significance of that cannot be determined right now. You have to do far more work to understand what this is. What is clear is that the dipole in the quasars is not consistent with the kinematic interpretation of the CMB dipole. That's all we can say on the basis of the data. This can mean that there are additional contributions to the quasar dipole that do not affect the CMB. One could imagine ways that could happen. People have speculated, for example, about horizon or super horizon scale perturbations. In fact, Jim Gunn gave a talk at an astronomy meeting many years ago in which he talked about isocurvature perturbations, because adiabatic perturbations, there will be a cancellation. And that is one way that you could reconcile them without abandoning the whole framework. Another possibility is that there is a fundamental directionality to the metric itself. Now, that is a much bigger step to take. And I think that we really need more data before we are in a position to be able to decide what way to go. We just need more data. This is just the very first step in reinventing the standard model.
So, I mean, like the CMB, sorry, can I ask one more in continuation?
We are out of time. So
okay,
anyway, we are going to have a discussion session after all talks. So shall we move to the next talk?
Thank you, Professor.
Actually, discussion session almost unlimited until George's colloquium this evening. All right, shall we move to the second talk?
Okay, I'll stop sharing my screen then.
Oh, yes. Yeah, thank you.
Thank you.
Chethan?
Yes.
Krishnan?
No, can you hear me?
Would you share the screen?
Can you see the screen?
Yes.
Okay, good.
Yeah, please go on.
So let me just make it full screen and then. So yeah, so let me start by thanking the organizers for inviting me here. And this is based on some work that I'm doing with my student Ranjini and also with Shaheen, who's in the audience. And it's still not completely finished, and there's some uncooked bits, but hopefully you'll get something out of it. It's not entirely, I wouldn't say that it is sufficiently original to fully make a complete paper yet, but hopefully there'll be something there which might be of some interest. Okay, so the starting point is that, and also please at any time if you you can interrupt and ask questions in case I am also my audio may not be completely clear. I think there is some issue with that, so if you cannot hear me, please let me know. So yeah, so the starting point of the observation that I would like to make is, which is a standard one, which is that ever since Copernicus we believe that the universe is we are non-privileged observers in the universe. And what that means is that we've increasingly taken more non-central place in our cosmological worldview, and the latest iteration of that is, in some sense, one can think of that as the multiverse. So so the way to think about that, and I'll qualify that in the next few slides, is that Copernican paradigm is supposed to be thought of as the idea that we are generic observers in some suitable sense. And what I would like to talk about today is this, to put some qualifications on it. And what I mean by that is that the notion of what exactly we mean by Copernican cosmology depends on our priors. And I will clarify what priors means in this context for me. In other words, generic should be understood as generic among a class of observers that are defined by our priors. So this is, I'll illustrate what this means in the case of standard FLRW as well as in things beyond in some sense. Okay, so yeah, so and the eventual goal would be, so I see some raised hands. Anybody has any questions? They can just ask it. I can't always see it. Is there a question?
Hey, Chethan, I think you're okay to keep going. We'll take questions at the end.
Oh, okay, good. All right. Okay, so yeah, so the minimal cosmological ansatz. So the goal of this program is this looking at changing the priors that underlie our cosmological or our Copernican paradigm, is that we would like to identify a minimal cosmological ansatz and equations of motion that allows the possibility of a cosmic flow in the universe. So this is kind of ties in with what Subir was saying a little bit ago. So this is sort of the goal, and I will present some metrics and equations of motion which might be of some use in this direction, and we can talk about whether it is how useful they might be. So so we will view this as a model building paradigm that is analogous to FLRW ansatz and Friedman's equations in a universe without a flow. Okay, so that's the sort of the grander goal. So yeah, so whether this paradigm is compatible with actual observations remains to be seen. It's just in the same sense that FLRW as it stands, you cannot really compare it against observations because you need a specific model within the paradigm. But one thing I find interesting is that in these models, the parameter that generalizes the curvature parameter K in FLRW, we will see is dynamically related to the fluid flow velocity parameter, which is sometimes called tilt. So it also showed up in Subir's talk in the previous the talk before this. So this may be encouraging. So that in some sense that would suggest that the near flatness of the universe may explain the smallness of the tilt. But again, this is, that's just by looking at the form of the equations which I will show you. And it may not, like the full dynamics has to be really evolved and fit with observations in a much more detailed way before it can really be thought of as a conclusive setting. So clearly more work is needed. Yeah, so so before I start for real, let me just emphasize my collaborators here. So Ranjini, who's my student at IISc, and Shaheen, who's in the, I think both of them are in the audience. And so this is work that we have been doing for, sort of half-heartedly for a while, but in the last few weeks it has sort of picked up because of this conference. So yes, and special thanks to Ranjini. Much of her hard work I will actually suppress in this talk, because I'll just present the sort of the result and not the details of it, which is kind of messy. Okay, so I'll start with this question, which is where we often start. What is the most Copernican universe? If there are no assumptions made other than the number of dimensions and the signature, what will be the most Copernican or most generic observer? How would we be the most generic observer in a universe where there's no assumptions made? And this idea is often encapsulated in the so-called perfect cosmological principle. And it states that we are non-privileged observers in both space and time, very crudely speaking. And one way to realize this would be if our universe was maximally symmetric. And a maximally symmetric space-time, I mean, it doesn't have to necessarily be maximally symmetric. For instance, an Einstein static universe could also fit a perfect cosmological principle. But one way in which it could do that is if it was a maximally symmetric space, like Minkowski or something like that. Space-time, maximally symmetric space-time, like Minkowski or something like that. So, but we know that that is not, it does not work, essentially because we know that the universe is time-dependent. Ever since Hubble's observations, we know that the universe had a Big Bang, and or the universe is expanding, and there is strong evidence for the Big Bang and so on. We don't want to question everything. So it seems like the fact that the universe is time dependent, I think, is an unquestionable assumption, unquestionable fact. So this leads us to revise the prior and only then look for the most symmetric ansatz. Okay, so the idea is that like we started with the initial assumption that the universe could be absolutely the most symmetric one. Any point in the space-time was just like any other point, and then we would end up with something like a maximally symmetric space-time. But that's not good enough because we know that the universe is expanding. So then we go back and revise our prior and then look at the most symmetric ansatz that is consistent with an expansion and with a time dependence. And this philosophy is what I'll mean by a Copernican paradigm, and that we will apply that again in the context of when we want to look at a flow. So this is what I will mean by revising our priors. So this philosophy, so we look for, so the idea when in the FLRW context was that instead of looking at a maximally symmetric space-time, we look for the most symmetric space-time that is compatible with our prejudices and priors. And in that case, when you just had to worry about time dependence, the natural guess would be that the universe, the spatial geometry of the universe was symmetric. Every point was equivalent to any other point. And the minimal, that is the most Copernican guess here, would be that the spatial slice is actually maximally symmetric. Okay, so this is what we call the cosmological principle. And maximal symmetry on a spatial slice basically means that there is a group of symmetries of dimension 6 acting transitively on the spatial slice. None of those words really matter too much. It just means the most symmetric spatial slice. And if you make that assumption, it just means that we have an FLRW universe. So the cosmological principle of maximal symmetry on the spatial slice is equivalent to the assumption of FLRW. So so you see that so the thing that I want to emphasize is that there is a sense in which we started with a certain Copernican paradigm based on some priors, and then found that, oh, okay, if you do that, then you don't find the best, basic prejudices like expansion of the universe cannot be fit in that. Then we go back and revise our priors and then look for the most Copernican ansatz within this new paradigm. So, and that gives you FLRW. Okay. But in today's talk, I want to investigate the possibility that the universe may have a flow which is responsible, at least partially, for the CMB dipole. And the motivation, we heard it in Subir's talk in the previous talk. And there are many papers by many authors, and I'm certainly not an expert on them. So I'll just cite my collaborators here for the first, for some of these works, which made me aware of some of these things. And also I will point to Subir's own paper, which was about the quasar thing that he talked about, which is the first time it kind of entered my consciousness. So yeah, it's kind of what made me think about the seriously as a theoretical possibility, at least somewhat seriously as a theoretical possibility. So there are also previous other works which I think are also relevant in this context, but apologies to many authors who may also have priority in similar observations. I'm just, please don't mistake my ignorance for, malice. So, so the idea here is that it seems that there is a cosmic flow in the universe which extends far beyond this our local neighborhood and probably extends to redshifts of order 0.5, 1, maybe even beyond. And if that is the case, so the question then is, even though this dipole is this flow seems tentative, we can ask the question, at least at the theoretical level, what happens if we take the possibility that the CMB dipole is not entirely kinematic and is the result of a cosmic flow? What happens if you take it seriously? How should you go back and look at this Copernican paradigm? How should we revise it in order to incorporate it, if at all it can be? So this is the question that I want to ask, and I'll have some sort of answers for it. You can judge for yourself how good they are. So, and yeah, it's some of it will not be too surprising for some of you. So yes, so we'll need to revise our Copernican ansatz from FLRW to one that incorporates the flow. And if there is a flow in the universe, how should we revise our priors? This is what I just mentioned. And the question is, what is the most symmetric ansatz that is compatible with a cosmic flow, which is sometimes also called a tilt in some contexts, in some spatial direction, but also it has an expansion in the time direction. So we know that the universe is expanding, and we suspect that the universe might be has a spatial flow in some particular direction. So let's take that spatial flow seriously, and then what is the geometry, what is the ansatz, what is the analog of FLRW that one might write down for such a universe? And we can call it the special cosmological principle or a dipole cosmological principle or something along those lines. Okay, so and I'll just tell you the answer. I mean, so there might be some small caveats to this, and I will talk about some of these caveats at the end of this talk. But so the key statement, so the primary statement that I'll make here, modulo those caveats, is that the most symmetric generalization of FLRW compatible with such a flow is one where there is an axial isotropy. By an axial isotropy, I basically means that there is a spatial direction around which the universe has a U1 symmetry, and spatial slices are homogeneous under a group of dimension 3. Okay, so if you're not well versed in what homogeneity means, homogeneous does not necessarily mean it does not automatically imply that so around every point the universe is isotropic. So homogeneity just means that you can move from any point on the spatial slice to any other point, and if you have a 3-dimensional group, that can do the job. So and slightly more technically, and so slightly more technically, our fluid, you can ask me questions if there are any. So it's about this. So our fluid spacetime has a preferred spatial direction around which it has an axial isotropy. And this axial isotropy is sometimes called, in the works of Ellis, which I will draw upon, they're sometimes called locally rotationally symmetric, but I find axial isotropy to be slightly more, natural word. So I'm just using that because otherwise I get confused. So it has an axial isotropy, and it is of the type 5 Bianchi class, which is a certain class of anisotropic cosmologies, and the fluid flow is not orthogonal to the surface of homogeneity. So there is a few things to unpack there. So yeah, I mean, but instead of doing that, what I'll take questions at the end if people have questions about this. But yeah, so there's a precise statement that one can make. The only thing I need from that this green paragraph here is that there is a precise statement one can make regarding the symmetries and features of a geometry which has which of a spacetime or a solution of Einstein's equations which has a tilt of this type. So, and one can write down explicit metrics using this. And I also want to make one comment here, which is that I call this a type 5 Bianchi class, but it turns out that when there is an axial isotropy, you can call type 5 and types, the type 5 Bianchi classes and type 7H Bianchi classes become identical. So this is something that is one can prove.
I'm sorry to interrupt. Did you mean axial isotropy or axial anisotropy?
Isotropy. Isotropy. I'm talking about a very specific spatial direction around. So what I want is So in order to get an anisotropy, I just need anisotropy not in the full SO3 directions, but I can still retain a U1 direction worth of isotropy, since observationally I have only access to the direction of the CMB dipole. So that direction is there, but I can retain in principle, given the data. So that's why I'm saying that this is a prior. There's a assumption about. So I'm trying to retain as much symmetry as I can, given the fact that I'm breaking. Along the dipole direction, something is going wrong, let's say. So that's why there is still an actual isotropy of a U1, but yes, I am breaking the full SO3 isotropy group of the standard FLRW geometry. I hope that answers the question. So yes, so right. So this is just a technical comment that type 5 and type 7H, when there is an actual isotropy, it basically gives you they are basically identical. You can rotate the the field binds into each other, the tetrads into each other, and you find that they're the same. So anyway, so there is a technical slide, and yeah. So I mean, I'm not an absolute expert on it myself, but I think that I understand it better than what I understood about 3-4 weeks ago. So if anybody has any comments on this, I'm happy to hear them at the end, and I'm also happy to take any questions at the end also. But the punchline here is that there is a specific category of space-times that I can write down based on this. And the metric basically takes a simple form. And this is actually a fairly standard form. So there are type 5 metrics have shown up in various places in the literature. So this is the form that the metric takes. But the key point is in the stress tensor, it's a bit of a mess. And it effectively takes the form of an imperfect fluid. And it is controlled by but the key point, because of our symmetry assumptions, it's controlled only by one extra function, beta. Okay, so this beta, which is what I will call the tilt, and therefore the equations of motion are quite tractable. So note also that this A naught here is in fact a constant, and this X and Y are just functions of Z. Functions of just T. So in practice, this is just, the only unknown functions are just functions only of the time variable, which means that we can, at least if the stress tensor is, since the stress tensor is also, as turns out to be just a function of time effectively, the equations that we will get at the end are ordinary differential equations of time. Yeah, so let me just write down. So I'll just quote, I'll just write down. I mean, I don't know whether these specific equations can be found in the literature, even though closely related ones do exist. Without tilt usually. So the first order Friedman equations are 2 in number, and instead of 1 you have, so usually this is this second equation is the one that usually becomes the standard Friedman equation, but instead we have 2 such equations. And note that there is 2 functions, x, y, this constant a naught and this beta, and you also have a mu and p. Mu is just the density of the fluid, and pressure is the piece of pressure. So and beta captures this tilt, and it's because of the presence of beta that even though in the underlying fluid is in some sense perfect fluid, the stress tensor that shows up on the right hand side of Einstein's equations turns out to be an imperfect fluid. Okay, so and I'm keeping the cosmological constant separate. So the mu and p are perfect fluids, and the lambda is just a is an extra thing. It could also be interpreted as a perfect fluid, but I want to let the matter that is sourcing Einstein's equation to be able to have a beta. Lambda doesn't have a beta because it doesn't break any symmetries. Okay, so this is my generalization of the Friedman equations, both of them. And then I also have the second order equations that you typically have in the context of Friedman equation, the second derivative equations. It's more like the second derivative equation plus the first integral type of, it's more like that. But anyway, so this is the second derivative equations that you have. And here also, instead of just one equation, you have 2 equations. Okay, so you have 2 equations here. So this is the claim is that this is a complete system. So this, instead of the 2 equations that you typically have in the Friedman equations, first order and second order equations, you have 4 equations, this is again first order and this is again second order. And the key point is that what we did when we went from the standard Robertson-Walker or FLRW to this metric is that we introduced one new function x. So we have one extra function here, and also I have an extra function beta, which is also a function of time, on the stress tensor side. So I've introduced two unknown functions. And so it is natural that I get two extra equations that determine them. So that's what has happened here. So instead of the two Friedman type equations, I have four Friedman type equations, Friedman, generalization of those. So, and I can also write this, the second derivative equations, I can exchange them for some conservation law type stuff. And I have written them here for your viewing pleasure. But yeah, I mean, it's doesn't really add much. It's just the same type of thing. And this W and this R that I have introduced here are basically, you can define them in this way. Okay, so this is, if for instance, this first equation here, the second equation becomes trivial when we go to Robertson-Walker. The first equation just reduces to the standard conservation law written in a slightly fancy way with some integrals and all that. So that's what these equations are. Okay, so this is my set of equations. And in principle, I mean, that's really kind of all I had to say. I mean, we have not really explored much with it. So, so we have two extra quantities. So one extra scale factor and one stress tensor quantity beta. And to accommodate for these, we have precisely two extra equations. Okay, and when beta equal to 0, one can yes, go ahead.
We do have this curvature. Can you show explicitly where in the equations it appears?
So that shows up in A naught. So this
Okay,
A naught. So there is, yeah,
but
so
in
this
the
A
equations.
Naught, sorry, go ahead. So can you repeat that?
Okay, so in the equations. Okay,
so for instance, here, so this is a curvature term, and also here, if you look at it. So this you can think of as like a generalization. I mean, essentially the Friedman equation. This is what becomes the Friedman equation in the FLRW literature. So this is this guy here is the curvature term. Yeah.
And roughly this x is 1 over x is 1 plus z, redshift, roughly.
So yeah, so I don't want to make, so questions of how to do cosmography with it is something that we are just thinking about now, because I think cosmography and redshift, I'll have some comments about it. So the point is that this is anisotropic, right? So how to define redshift, a meaningful notion of redshift, etc. I think I still have to think about it. So I think, yeah, let me make, I mean, you can ask this again. I think that maybe that's better.
Okay.
Okay, so yeah, so
actually,
first,
Chethan, can I ask a quick question? So in Bianchi 7, you have a H parameter, right? I guess it's a constant, right?
Right.
Where does that fit in here?
So when A naught
absorbed
is,
it.
so that A naught, so when A naught is, so A naught basically captures that very roughly. So if A naught is 0, that H becomes 0. That 7H, type 7H Bianchi, there's a parameter. That parameter basically goes to 0 when A naught is 0.
Okay.
So, yeah, so, but yeah, so I mean, my student Ranjani is probably in the audience. I think she's like the Bianchi expert. I'm not really like, I'm an amateur. I just started doing it recently. So feel free to comment, Ranjani. So if you have any comments, please feel free to interrupt and comment. Okay. So yeah, so when beta equal to 0, one can consistently set A naught equal to 0 and set, this to get FLRW equation. That's kind of like a 0th order check. And this I already mentioned as an answer to the question. And note that the assumption of spatial homogeneity means that Einstein's equations are still ODEs, and that's the major plus as I see it, if this thing is of any use at all. So is that if it is an ODE, you can do things with it. It's not a PDE, and yeah, so the system is very tractable. Note also that in principle the equation of state can be arbitrary and can allow mixtures, because I've left P and mu, P and rho, I call it mu, but the pressure and the density, they are essentially arbitrary. So the same freedom that you had in the case of FLRW is still very much there. And so the question is it worth trying to build models here? So in order to see whether this can fit the, a realistic or at least quasi-realistic models, something that at least, maybe it's not a competition for LCDM, but at least we can try to maybe get it to.
Chethan?
Yeah, go on.
You have roughly 5 minutes.
Oh, okay. So I'm basically more or less done. So yeah, so I just want to give credit where it is due. We can get these results by specializing and translating some general results from the late 60s and 70s by Ellis and some of his collaborators. So especially Stewart and King, with these people there, with the papers that he has written, are the ones that we have found useful. But this particular specialization of their results looks quite well motivated to me because of this Copernican symmetry argument that I mentioned. So this is perhaps why it's maybe worth a systematic exploration of fluid models in this context. So note also that we were able to write them in a very simple metric form. And in LS, you might, if you open some of these papers, it is usually phrased in the language of field binds and spin connections and all that. But on the other hand, in this particular case, it actually simplifies very nicely, and you get like a purely metric kind of setup where you can play around with mathematics and so on. So, and the primary concern, to give put some context on this, the primary concern of the Ellis papers is with situations which have less symmetry than what I am talking about here, and therefore they generally deal with less Copernican spacetimes according to our criteria. And so, for instance, in Stuart Ellis, they assume axial isotropy, the U1 symmetry that I mentioned, which they call local rotational symmetry, but the spatial slices are not homogeneous. And so technically what that means is that there is a non-trivial isotropy group around points, but no demand of spatial homogeneity. And in King-Ellis, on the other hand, they keep the spatial slices homogeneous, but they work without axial isotropy. And what we want is we want a combination of these. And that's what we have basically done. So yeah, so it's in some sense, it is a slight simplification, but combination of both of these papers. So an Ellis-McCallum does not allow tilt, but it's a good point of entry into this kind of stuff if you are interested in looking at it. So yeah, so what next? So all we have written down in this talk is the simplest and the most symmetric perfect fluid model that has a non-trivial flow. That's all I have done. I've not done anything with it. So how do we fit it to the data, if at all it is possible? So zeroing in on the flat LCDM required not just observations of the background, but also of CMB anisotropies. So that's how we fit the lambda CDM model, the relative abundance of the various matter forms and all that. So in other words, we need perturbations, and here it is not very clear whether how much perturbations we can do. So yeah, so various special cases of this type of equations that I've written down have, you can find it in various people have done anisotropic cosmologies, but usually with specific matter like scalars and usually without tilt. Okay, and no real attempt at matching with actual phenomenology by choosing appropriate mixtures of equations of state seems to have been made. And my primary interest, even if it turns out not to be very interesting from a phenomenology point of view, is that this class may be worth exploring to get intuition, because it's a very simple setup. So it's a very good, good setup to get some intuition for cosmography and anisotropic notions of redshift, all of which we kind of will need to understand if there is a real, cosmic flow in the universe. And so there is a paper by Asta Heinesen that I kind of noticed, which might actually be useful. So I think it's a more, she addresses a more general question, but I think it will probably be easy to adapt that to our setting where this metric is extremely simple. So, our class is analogous to FLRW as a class, and that it can, as I already mentioned, and yes, there's some relation to work with sagas, which unfortunately I don't have time to really talk about, even though I also don't have much to add there. So yeah, so in lieu of a conclusion, I'll add two caveats. So the symmetries only allow one function for the tilt beta, but note that we can in principle have multiple components of matter. So it is not clear how natural it is to have all matter have the same tilt. This is something that is not very clear to me. My suspicion is that this beta should be viewed as the tilt that one should associate with the dominant form of matter at that particular epoch. I think if that interpretation can work, maybe this is a useful setting for investigating things. And yeah, so this slide is, this is one more caveat, but maybe not a big caveat. So, so how much time do I have? Yeah, so I think I've kind of run out of time, so I'll just leave it there.
Yeah, thank you for your talk.
Yeah.
And shall we have one short question and postpone all questions to discussion session? All right. Dominic, short question.
No. Yes, thanks a lot for your nice presentation. One short question. So why do you think we really need to go beyond the scheme of perturbing Friedman, Robertson, Walker? Because all the evidence we have for this arc flows and so on, they are still at the percent level only. Yeah. They are not order one effects, right?
Yeah, I agree. I think that's yeah. So so my point is only that if you want to really do perturbation theory with this background, then we only have U1 isometry. Then it is yeah. Technically, it will be a challenging problem. But I do agree with you that if in these models we can find solutions which are close enough to the FLRW, LCDM type of setups, which I mean remains to be seen. I'm just wrote down some equations. I don't know whether they really are, can fit that. But if they do, yes, I think at the pragmatic level, maybe it would be okay to just do the perturbations with FLRW and treat this as a perturbation. That may be possible.
Hey, Dominic,
maybe,
just Dominic on that. We're seeing variations in H0, right? So it's sort of hinting at a background thing.
Yeah, that's true too.
I mean, of course, somebody would need to go through the details, but.
So I just want to add one thing, which is that at the technical level, because the symmetries are less here, if you want to do perturbations here, it would be hard. It would be a background level. I think this is not so much more harder than FLRW. But if you want to do perturbations, I think that because we only have a U1 symmetry, the usual scalar tensor vector decomposition is going to be significantly more complicated. But yeah, that's just one thing.
Eowyn, shall we move to the third talk?
Yep, you're in charge.
Yeah, we have a longer discussion session after Alexei talk. Konstantinos, would you share your screen?
Sure. I am unable to turn on my camera actually, but
1 second, sorry, just give me a second.
Yeah, that's fine.
and also it tells me that host disabled participant screen sharing.
Okay, now you should be able to. Sorry.
Okay, yeah, I can turn on my camera now. Okay, now everything works perfect. Thanks. So, okay, hello everyone. My name is Kostas. I am a postdoc at the University of Bonn. I want to thank the organizers for inviting me and putting together this very interesting meeting. So my talk will focus on galaxy clusters and what can they tell us about the isotropy of the local universe. I will start with what else, the cosmological principle, but since there was an extended discussion, there will be an extended discussion. I'll just stick to the basics. So what does the cosmological principle mean for the local universe? The isotropy property means simply that we should measure the same expansion rate, h0, towards all directions in the sky. The homogeneity property, an assumption, means that the universe must hold similar amounts of matter, averaged over large scales everywhere. And this, consequently, this means that no strong bulk flows should be observed for scales larger than 200 to 300 megaparsecs. There were already discussions about that, what a bulk flow is, so I'm not gonna go through it in detail. I will just say that it's pretty much an average peculiar velocity of all the objects within a cosmic volume. And what it means for our clusters, though, it means that when we measure the redshift of all the clusters within a bulk flow volume, let's say, we misinterpreted their distance because we measure the redshift, but this redshift is a sum of the cosmological redshift due to the Hubble expansion and of the peculiar velocity redshift. If we do not take this into account, we get the distance from the measured redshift. This distance propagates on the cluster properties such as X-ray luminosity, for example, and all these cluster properties for the objects within such bulk flows are systematically biased. Now, the question is, how can we use galaxy clusters to test the isotropy of the local universe? As you all know, galaxy clusters are the largest gravitationally bound systems in the universe. They contain up to thousands of galaxies, vast amounts of dark matter, but the most interesting component for us is this hot intracluster gas that they have between their galaxies, accounting for 10 to 15% of their total mass and reaching temperatures up to 100 million kelvins. So this gas mostly consists of free electrons and protons, and their interactions can be detected in X-rays and in microwaves. In X-rays, galaxy clusters can be observed through the so-called Bremsstrahlung emission or free radiation, which produces photons with energies of 0.1 to 10 keV. And what we can do is simply observe a galaxy cluster, measure its flux, so how bright it looks here from Earth, measure its redshift, assume an h0 value and other cosmological parameters, go from the redshift to the distance, and then using the flux and the distance, we can get the X-ray luminosity of a cluster. Now, galaxy clusters can also be observed in microwaves through the well-known Zhunev-Zeldovich effect, which is simply an energy boosting of background CMB photons as they travel through the intra-cluster medium by free electrons in the cluster. And as a result, when we observe the CMB towards a cluster position, we see a spectral distortion of the CMB. The amplitude of this distortion traces the thermal state of the intra-cluster gas. And if we take into account the physical size of the cluster, we can actually determine this quantity here, the total integrated Compton parameter, Y as Z, which scales together with the mass of the cluster and other properties. Now, in order to get the physical size of the cluster in kiloparsecs or in megaparsecs, we need actually to measure its apparent angular size in the sky. And by, again, assuming an H0 value and using the redshift, we can get the angular diameter distance. One can measure many things with clusters. That's the fascinating thing about them. We can also measure the luminosity, the infrared luminosity of their central galaxy called LBCG, which is, being a luminosity, is also cosmologically dependent. Or we can measure also the effective radius, the X-ray effective radius, which is the half-light radius of clusters, again in arc minutes, and using an assumed H0 value on the redshift, we can get this radius in a physical size in kiloparsecs. Now, the most important measurement for our study is the cluster X-ray temperature, because, as you will see, is independent of any cosmological assumptions. So this is the #1 measurement that we need for performing this test of ours. In order to get the temperature, we simply observe a galaxy cluster, extract its spectrum, fit the appropriate thermal emission models, and as simple as that, we have the temperature of the intra-cluster gas. Now, within this process, cosmology enters nowhere. So again, it's very important to stress here that the temperature determination is cosmologically independent. Now, we have all these 5 measurements that I described for the A high flux cluster sample, which is a homogeneously selected sample, covers the sky pretty much uniformly, except for the galactic plane here where we put a mask. And it contains clusters mostly at redshifts below 0.25, so it traces the local universe. It also includes the brightest X-ray clusters in the sky, which means very good photon statistics. And we have precise temperature measurements for 313 of them. Now, the key to all that, the key to our study, is the cluster scaling relations. Scaling relations are quite easy to comprehend, actually. So let's assume we have a cluster with a higher mass. This would mean that it's also bigger, so a larger effective radius. At the same time, it would mean a deeper gravitational well, which would lead to higher gas temperatures. Also, it would mean a bigger galaxy in the center of the cluster, which is also more luminous. At the same time, higher mass means more material, more ionized gas, more emitted photons through the free radiation, higher X-ray luminosity. And similarly, with a similar train of thought, a higher YZ value. So cluster scaling relations are theoretically motivated and have been well established for observation for more than 2 decades now. And they're just simple power laws that relate all these different quantities with each other. In our work, we have studied 10 multi-wavelength cluster scaling relations among the 5 properties I described before. 5 of them actually have been presented in the literature for the very first time from our work. And each scaling relation can tell us something different about the local universe. The most valuable scaling relations in terms of cosmological information are these 2, the LT relation and the YZT relation. So what we do now is simply measure the temperature without assuming any cosmological parameters, because we don't need to. And we have the right part of this equation. The slope we know because it's completely independent of the H0 value. So we have this right part of the equation, again, without assuming any cosmology in the process. Now on the left part, for the luminosity, for example, we have the flux, we have the redshift, and now H0 enters in order to get the distance. So we can play around with the H0 value in order to make the left part of the equation match the right part. Similarly, we can play around with the redshift and bulk flow motions that we can model and see what such motions are found by our data. Now, doing that, especially the H0 variation, doing that for different parts of the sky, like you can see here. For example, we get only these clusters, we perform this test, then we get only these clusters, we again repeat this test. We can actually obtain an apparent H0 value for each direction in the sky, and we can plot it color-coded in the middle of these cones here. And this results in the color maps that you will see in a few slides. Now, I have to stress here that this is a novel and completely dependent method from anything that has been done in the past. And it's a very powerful method, as you will also see, which has led to 3 peer-reviewed publications. The 2 most recent ones you can see here. And for these ones, I will talk about next. Now, to the exciting part, to the results. Let's start off with a LT relation. As you see here, the correlation between the luminosity and the temperature of clusters is very clear. And here you can see that we have plotted other results from other studies, from other measurements, completely dependent work from ours. And all pretty much agree with each other, which tells us that we did a good job measuring these cluster properties. Now, the question that we are all here for is what the LT relation can tell us about the apparent H0 spatial variation. In order to determine that, we use the E high flux cluster sample, which I described, plus 2 other completely dependent all sky cluster samples to each other and to E high flux, but not as important as E high flux. And now the question remains, do clusters trace an isotropic expansion within the CMB rest frame as the lambda CDM model tells us that they should, and the cosmological principle? So the first indications point that that's not the case. So from the LT relation alone, we see a very clear spatial variation of H0 on the degree of 10%, ranging from 66 to 73 for the rest of the sky here. And following actually a very conservative statistical approach with Monte Carlo simulations, we found that there is a 3.5 sigma tension for these observations. Also a very interesting feature here is that if we plot the directions of other studies, completely dependent to our own, using quasars, supernova galaxies, there are studies that do detect anisotropies, and they usually detect them towards the same preferred axis with our study, which is really exciting. The question now is, of course, what could actually cause the anisotropies that we measure with the clusters? We have identified 3 main culprits, let's say. First, it's an excess X-ray absorption creeping in our measurements due to previously undiscovered gas or dust masses in the galaxy. Here, I need to stress again that we do correct for the known absorption effects, but who knows, maybe there are stuff in our galaxy that we haven't discovered yet and that they mess around with our measurements. We have performed many tests also in the first paper that show that this is highly unlikely, but I will talk about that later on. But this is still a valid scenario for now. Now, a second explanation could be a large bulk flow motion that messes around with the redshift estimation, the distance estimation, and eventually the luminosity estimation, making us think that it's an H0 anisotropy. And the third scenario is, of course, a possible anisotropy of the expansion rate of the universe, at least up to scales of 800 megaparsecs, which is the scale that our clusters can trace robustly, let's say, because after that, we do not have enough data to perform this test. How can we tell these 3 scenarios apart? We have to employ other scaling relations out of the 10 I showed you before, with completely different sensitivities to cosmology and to other systematics to discover the cause of these anisotropies. By far the most useful scaling relation for our study is the Y-Z temperature scaling relation, because it has pretty much the same number of clusters as the LT relation, but it has a much lower dispersion, a much lower scatter, meaning more precise constraints. Also, being measured in the microwave bands, it's insensitive to galactic absorption. So YZ has completely different dependencies on the galactic material than the X-ray luminosity. This means, due to these completely different dependencies and sensitivities, that if we see the same anisotropies this time as we did for the LT relation, this would be a very strong indication that the origin of these anisotropies are cosmological. If we do not see the same anisotropies this time, it would mean that something is wrong with the X-ray luminosity measurement, which would point towards an X-ray absorption related answer to the anisotropies we have detected. So it's completely fascinating then, considering the above, that we see exactly the same anisotropies, exactly the same H0 variation here, ranging from roughly 64 to 73 for the rest of the sky. But we have a higher statistical significance this time because we have a much lower dispersion. Now here you can see the first ever Hubble diagram using galaxy clusters. And you can see here, for example, the Y-Z-T relation, that the blue points are systematically above the red points up to the scales that we can actually trace. Another piece of information that we can obtain is by using the infrared luminosity of the central galaxy versus the temperature. The problem with that is that the scatter you see here, it's huge. So no safe conclusions can be drawn only from this relation, since the anisotropies do not exceed 2 sigma. So this map is practically consistent with isotropy. However, you see that even this 1.9 sigma anisotropy is found again in the same region as before. So by stacking everything together, the X-ray information, the microwave information, and the infrared information, which are very nearly independent of one another, we can actually improve our statistics a lot. And that's the fascinating thing, the exciting thing about galaxy clusters, that they offer you more than one way to actually trace cosmology. Just one object tells you more than 3 to 4 things about cosmology. So by combining all these different results, we create the first ever multi-wavelength H0 anisotropy map of the local universe, which you can see here. So since the 3 maps agree, LT, YZT, and LBCGT, it's expected that the statistical power will increase. So you see here that we are able to reach nearly 6 sigma anisotropy in this map, which has been assessed using Monte Carlo simulations, and which is by far the highest, the strongest signal of an anisotropy ever obtained in the local universe. You see here that the obtained map is very, very smooth, and again points towards the same direction from 66 H0 roughly up to 73 for the rest of the sky. And here you can see the preferred axis. Unfortunately, our direction uncertainties are still quite large, but I promise you that we will fix it in the future with better measurements. Now, we have to ask ourselves though, what happens if actually the expansion of the universe locally is isotropic? So what could actually cause these things that we observe? The answer to that is a large bulk flow. So in order to quantify that, we use many different redshift limited spheres, redshift cells. We take the full sample every time, fit the scaling relations with 2 additional parameters, the direction of the bulk flow and the velocity of the bulk flow. And as such, we obtain a bulk flow amplitude and direction for every redshift limited volume. Here, you can see our results. In the y-axis is the bulk flow amplitude, and on the x-axis is the radius of the sphere we are considering around ourselves, and on the right part is the median redshift of independent cells we are considering. In order to quantify the bulk flow, we have employed different scaling relations, different and independent samples, and different statistical approaches. And we see that every time we obtain a very consistent signal of a bulk flow, which points towards a 900 kilometers per second bulk flow, extending up to at least 500 megaparsecs or redshift 0.12, because this is the scale up to which we can actually constrain things meaningfully. The interesting thing is that, regardless of the redshift range we are using, the directions are pretty consistent here, as you can see, of the preferred axis of the bulk flow. Now, the bulk of our work is actually focused on keep looking for alternative explanations having to do with systematics. Because when you find something so exciting, to put it at least, you have to make sure that no biases are creeping in your analysis. I'm not going to bore you with that a lot. So the most important thing that we tested is again X-ray absorption effects. So here we have the advantage that the other scaling relations can unveil to us many different things despite cosmology, such as absorption. So we have performed 4 different tests that each of these tests can robustly detect excess X-ray absorption, so the real X-ray absorption, not the one that we only correct for, in order to see if there is any indication that something goes wrong in this mysterious direction that we find. So not even one test out of the 4 unveiled even hints of X-ray absorption towards that part of the sky. So I'm very confident when I tell you that excess X-ray absorption does not have an effect in our results, which we already kind of knew because of the anisotropies in the YZ relation. But now we are completely sure. We have performed actually many tests. So we accounted for the morphology of different clusters and the effects that this can have in the anisotropies. We account for Malquist bias. We performed simulations to assess the bias inserted for this galactic plane gap that we have in our data. Apparently there is none. We have actually used different selection cuts in our data to see if there is a very specific cluster population that causes this. It's not. We have accounted for the scatter correlation between these 2 parameters, which are not completely independent, but they are weakly correlated due to the physics going on in each cluster. But we have taken this into account. We performed my favorite test of all, an MCMC analysis based on cosmology independent measurements of clusters, based on which we can actually predict the H0 behavior of every cluster region. And it appears that for cosmology independent measurements, the sky should look pretty much isotropic. So the observed anisotropy should come from a cosmological reason and not the systematic. We have accounted also for the temperature calibration between the XMM Newton and the Chandra X-ray observatories. We have studied the Eddington bias, and we have performed 10 million Monte Carlo isotropic simulations in order to see how frequently these anisotropies can pop up randomly in an isotropic universe. And the 6 sigma anisotropy I reported earlier is based on these Monte Carlo isotropic simulations. So no matter what we did, we couldn't find an explanation for the observed anisotropies. So for now, at least, it really looks like there's an anisotropy in the local universe of H0, which would contradict the assumption of isotropy, or alternatively, there is a large bulk flow motion, which is not completely not expected in a lambda CDM and would need a huge matter inhomogeneity to explain. So this brings me to my summary. All in all, we developed a very powerful new method to scrutinize isotropy using galaxy clusters in the local universe. And when we do so, we observe these very strong local anisotropies exceeding 5 sigma, which could either mean a local H0 anisotropy or a large bulk flow. Both of these scenarios strongly contradict concordance cosmology, but we are far from done. We are already planning how we can improve our data, improve our constraints, use larger samples to find what's going on. And I promise you that in the next few years, we will have a definite answer about that. Thank you very much.
Thank you for your talk. Question, first, Noam.
Hi, thank you for taking my question. My name is Noam Liebesken. I was wondering about the size of your sample. So you had a few hundred clusters, which is not a huge number, and then you're dividing them into different sort of hemispheres. So my question was really one, what is the expected variation in the computed H0 when you subsample what is already sort of a small data set? I don't mean that in a mean way. I mean, I'm just used to galaxy catalogs with larger numbers. So if you compute H0 in one direction as a function of sort of opening angle and you do it over and over again in the sky, what's the expected variation that you should get?
Right. That's exactly what we wanted to test using the Monte Carlo simulations. So the expected variation is far from what we see. So here you can see actually our sample. We have roughly 560 clusters. And so in order to answer the first part of the equation, the advantage against, let's say, supernova catalogs are that they are very uniformly distributed. So this actually increases the statistical power of our analysis. However, we do expect some variation when we just sample an isotropic universe based on the exact same data, based on the number of data on their positions. But usually we expect 1 to 2 sigma detected anisotropic sample, anisotropic signal from an isotropic sample of the same size as ours. So not a 6 sigma one. But the good thing is that eROSITA will be available soon. So we'll have, instead of 500 clusters, we'll have 5,000 clusters within the next 2 years or so. So our analysis will improve dramatically. But nevertheless, this number of clusters is already enough to have conclusions about the very local universe.
Thank you.
Next question to Subir.
Hi, Kostas. People believe that the Sunyaev-Zel'dovich measurements by Planck have ruled out bulk flows larger than perhaps 400 kilometers per second out to scales of, say, 300 megaparsecs. Can you comment on the consistency or lack of it of what you find with their conclusions?
Yes. So that's a very interesting question. The problem is that in order to actually conclude that something doesn't happen, it has to be traced by independent methods, right? So it's the Planck measurements again that point us to a bulk flow here. So the method they are using from the KSZ signal does not point to a bulk flow, but is their own measurements that do point to a bulk flow here. So if you see the YSZ T relation, for example, which are the red dots, the Planck measurements are the one that point to a 1,000 kilometer bulk flow up to redshift of 0.1.
That's exactly what puzzles me. So from the same data, they concluded an upper limit.
So I like our analysis because it's very simple. So it's just an empirical analysis. We just take advantage, we exploit the correlation, a very simple correlation between the Planck values and the temperature, and we just see how much we would need to correct the redshifts for in order to get an isotropic universe. So I would say that our analysis is much simpler than the Planck analysis, but I cannot say it's the correct one, of course. Maybe we have done something wrong, I don't know. But future analysis will tell.
Thank you.
Shall we have the third question from the participant, Stephen Angus? Do you hear me?
Hello. Yes, I have a brief question. Thanks for the nice talk. I was wondering, so maybe you know there's this soft X-ray excess emission in galaxy clusters. I was wondering if that can be accounted for by this in this analysis, or if you made any assumptions on that. Can you comment?
So the simple question would be, I'm not quite sure how this could affect our results, because when we measure the X-ray luminosity, we just measure everything. But I don't see the reason why in an isotropic universe, 100 clusters towards one direction would have higher excess X-ray emission than 100 clusters to the opposite direction. Since this is an intra-cluster physics mechanism, it should be pretty much the same everywhere. So if you statistically sample big number of clusters, large number of clusters, this should cancel out. So what you are referring to is probably the cool core problem. So there are clusters based on their morphology, but they are more luminous for the same temperature. But we do take that into account. It's the morphology test that I referred in the slide with all the tests. So we trace actually the state of every cluster, and if it shows this excess X-ray emission, and we see that statistically the populations of clusters are similar everywhere in the sky, so we don't have to worry about that. But actually, that's what I'm working on right now, is to measure the luminosity by excluding the cluster region, which causes what you are referring to, in order to get rid of this possible problem, let's say, and significantly decrease the scatter. So yeah, I hope that covers your question.
Thanks. Yeah, just briefly. So did you see any directional dependence on this excess, or is the sample size too small to say?
I'm very happy actually that you asked this. Yes, I have a backup slide of that. There is a small dependency but not more than what would be expected by just noise. So you can see here, this is the fraction of disturbed or relaxed clusters, or in other words, non-cool core and cool core clusters. And there is absolutely no correlation with what we find. It's not important anyway, because this effect doesn't affect the YSZ measurements from Planck or the LBCG measurements. So it's just a matter of an interesting discussion, but it doesn't enrich our results. Nevertheless, there is no correlation of this excess here with what we find here.
Okay, thank you.
Okay, the last question by Shahin. It's a short question.
It's a very short question.
It's a short question.
So can you comment also the implications of your findings for H0 tension?
Yes, that's a very interesting topic actually that I'm planning to pursue very soon. So as you know, so this has to be done analytically, right? So whatever we discuss now is just a matter of assuming. But the H0 tension comes mostly from supernova samples. Other probes also point to that, but the 5 sigma tension is due to the supernova. And we don't really have many supernova towards that direction here. So it could be qualitatively, at least, it would seem to me that if we don't have any data here, and if these anisotropies are true, then an overestimated H0 could occur from supernova. However, this is just a qualitatively direction of the test. We have to do it with numbers in order to see if there is actually an effect on that or not.
All right. Thank you for your talk and also answer to questions. Shall we move to the last talk of this session? Professor Alexei Starobinsky. Alexei, good to have you. Yeah. Shall we welcome Professor Alexei Starobinsky? He'll talk on modern cosmology. Does modern cosmology need the cosmological principle as principle at all? Alexei, please go on. Alexei, do you hear me?
He's good. Alexei, you're muted.
All right, all right. Would you increase your volume? Increase your speaker volume. All right.
Can you hear me?
Yes, good.
Okay, now let me share screen. Okay, can you see my slides? I can make them slightly larger. Okay. Okay. Thanks for organizers for inviting me to this very interesting workshop. And actually, the main reason why I wanted to say something, there will be some new things regarding possible variations of form of the standard model at the end of my talk, but the main reason was just the title of this workshop, a discussion on the cosmological, and that's why I would, because indeed there is some different opinions even in textbooks. Do we need cosmological principle as a principle at all? That's why I wanted first to present some very general remarks about why modern cosmology does not need to take this as a principle. So instead of this, so I would say, instead of principle, it's better to work with models, because we have models, principles are pretending to be very fundamental, while models are only approximate. Of course, where it can be corrections. Actually, what we heard in the previous talk are also, I would say, some 10% corrections. And so at the level of models, we don't need to change the paradigm. We have only to correct models. Okay, and then I would like to remind you about the simplest one, parametric inflationary models, and even according to these models, to these viable models, I don't want to say that no other possibilities are excluded. I say if we have some models, we can compare them observations. And from theoretical point of view, the simplest inflationary models existing now are only one parametric. That is, that they have to take only one constant, one actually which can be made dimensionless from observations. And I shall show you, remind you, actually, it's even a textbook result, but not so much emphasized, that you can what are the restrictions which are imposed on the duration, on the inflationary stage for the absorbed CMB anisotropy, and that's it. And finally, I shall tell about our recent result, which is beyond the slow roll approximations, and finally some guesses that still there may be some more in different fluctuations that we usually consider. So okay, so this is actually what is the main general statement of my paper, that the cosmological or Copernican principle played an important role about 150 years ago. Modern cosmology does not need it as a principle, that is something superior to concrete models, viable models. And what I mean by viable models, first, of course, they should be internally consistent, they should be predictive, so they should make some quantitative prediction, and that's why they're falsifiable. And it's, I would say, it's rather natural to compare that cosmology with another area of general relativity, a study of the physics of relativistic complex objects, and nobody tried to introduce black hole Kerr-Newman principle. So to say that it should be some principle that black holes should be only of a Kerr-Newman type. Okay. Instead, we have models. We have general relativity, which indeed predicts that there should be Kerr, or in presence of electric charge Kerr-Newman. We have alternative gravity models which may predict some different form, and these models are also can be tested by observations. And actually, it's using black holes. It's usually not the easiest way to take this alternative figures. So that's why once more, principle pretends to be for too much things. Models are always approximate, and what can be further developed. Okay, and so let's remind the standard thing that actually from what was the first hint for an approximate local isotropy and homogeneity of the universe. Of course, it's a Hubble law. It's a Hubble law. Of course, it's not exact. It's okay. It's approximate. And once more, we heard in the previous talk about some deviations, but still, in the main approximation, with as was mentioned, with approximately 10% accuracy, we have this law, and indeed we have some discrepancy, because this 70 plus minus 3 is not the error of any concrete observation. It includes just difference between different types of observations. Okay, we have general, once more, so once more, at the level of not principle, but at the level of concrete models, we have a statement about isotropy and homogeneity of the universe are approximate, so local universes, approximately isotropic and homogeneous, that follows from these arguments. And actually, we do not insist that it should be, once more, would we insist on the principle, we should insist that it is everywhere at homogeneous and isotropic, and it's not so, and we don't have any, I would say, we don't have any internally consistent model which predicts that the universe should be exactly anisotropy at all scales. In particular, just these simplest inflationary models which I present, they indeed does not have regular behavior at partial infinity. That simply follows from the fact that the prediction of the predicted perturbation spectrum diverges at small scales. Once more, so the best what we may have for models is some range, some finite range of isotropy and homogeneity, beginning, say, from few megaparsecs and up to very large scale. Okay, it depends on the model. In the inflationary model, it's very large. Okay, and these are standard arguments for anisotropy, so just let me only mention them. And arguments, and the first argument from homogeneity, it simply follows from the fact that the Hubble law has this dependence R, and not say R squared, but any other dependence. In this dependence, we have okay, you don't have for this law, so that the velocity, so at least local ones, are proportional to the first power of the distance. Is just it is just the form which is needed for spatial inhomogeneity. Of course, the unsolved problem is the exact value of H naught. I don't want to make any concrete statement, but I would say that just because the value of H naught refers to homogeneous background, homogeneous first, and from the point of observations local. And so I would only mention that once more, from the point of view that we are working not with the principle but with models, where one of the way from cosmological point of view is look what is the most questionable point of a standard model, and of course it's the assumption that the dark energy is exactly cosmological constant. Okay, if it's not so, then indeed many things will change. And that really, it seems that the most, just because all of this effect refers to recent redshifts, so that's why I would say that indeed, though, of course, there maybe exists some purely astronomical explanations for this effect, I would say that from fundamental point of view, the most interesting will be really that the dependence of present dark, the difference of a present dark energy from the exact cosmological constant, and in particular, would it really occur? New modes of inhomogeneities may well appear, and so from this possibility, in particular, effect presented in the previous talk may be rather natural. And I would say that the most dramatic that would be the discovery that the dark energy density, in fact, it grows. And because looking inside observational errors, still some tendency for its phantom behavior exists. And why I would say for me, it would be the most dramatic, because it goes just against expectations from modern variants of the fundamental quantum theory of everything, including the so-called savant lamp conjecture, which insists that there should be no stable dark energy, that if it either it does not exist or it should quickly decay. So would it will be discovered that indeed it grows, then it can falsify at least some models of the present dark energy. Okay, then I would like now I shall concentrate about some concrete models, namely the simplest variants of the viable inflationary models, and I count simplicity not by how simple are constructions which are standing in the equation, but a simple observational test, how much free parameters does this models contain, which cannot be obtained from theory itself and should be taken from observations. And my statement that from observations we need two constants, the amplitude of the power spectrum and the slope. In the simplest variance we can derive the second constant. And I shall also present you, it gives you some very strong quantitative argument about the degree of homogeneity of the universe in the inflationary scenario. Of course, during the inflationary stage, namely from the theory itself and observations, it follows that the duration of the inflationary state should be practically the same in different points of space inside our past light column. I don't want to discuss what happens outside our past light column. Okay, so let me remind you what I mean by variable models. Actually, I mean some subclass of all possible inflationary models, with slow rolling inflationary models, which are actually based on two independent assumptions. The first refers to the background. It's that it is a very hypothesis of the existence of the metastable quasi-de Sitter stage. And the second refers to the origin of all inhomogeneities of present universe. It is assumed that it is produced just from this effect, not from some other effect, creation of particles from the adiabatic vacuum state, not for all Fourier modes. That is not possible. As I said, it's not possible for very large scale, but for some range covering all observable range of scales. And that's why my remark that usually use terminology that we're in the Bunch-Davis state is actually not rigorous, because once more, Bunch-Davis state is the state in which this assumption about adiabatic vacuum is valid for arbitrary large scales. Once more, in variable models, it's not possible. So that's why all existing, at least the simplest inflationary models, does not predict regular behavior spatial infinity. Well, remark I consider as an advantage of the simplest inflationary models that assumptions of what was happened in the universe in the remote past, in the region of very high large cavities, they are not orthogonal to what we know from the usual physics, in particular the first hypothesis. The first hypothesis is actually at the quantitative level. It's just the assumption that the properties of primordial dark energy which produce inflation are the same from the quantitative point of view as the properties of present dark energy. Of course, we have to assume much more degree of instability compared to the present dark energy. And the second effect is just copies the theory of this effect, is just copies the effect of the location of electrons and positrons in the electric external field, which I would say almost confirmed. So that's why, as I said, we have models, in particular the simplest models, which I shall present you in the next slide, and what we expect from any models is the prediction for, is indeed the prediction that we can obtain at present. We can obtain a generic resolution which is sufficiently close to the locally to the Friedman to Walker phase, and then it appears that we always consider so the most interesting effect in these perturbations, and there always exists the statement. Yes, I shall present you some argument at the next slide. Among all possible perturbations, not only general relativity, but in a very wide class of modified theory of wavelengths, there should exist some what can be called constant modes. Constant mode that in this regime they are time independent, and when the trace part can be shown, you just consider what is called gauge invariant, or better to say local gauge invariant curvature perturbation, and but we also this matrix should have some traceless and transverse paths, and so for each inflationary models we expect also the predictions about primordial gravitational wave, primordial tensor perturbations, and the most important quantities to be compared with observations upper power spectrum, where slope is for only purely historical reasons. It is denoted not as simply an S, but an S minus 1, it's simply a notation. And also by the ratio. And the existence, as I said, the existence of constant modes, let me once more make a few remarks. Though it was for general relativity with ideal fluids, it was known already for Lipschitz when it was proved for modified scalar tensor gravity theory in this paper. But actually, once more, the existence is much more general and simply follows if any theory of gravity has isotropic Friedman-Robinson solution, if this solution is non-degenerate in the mathematical sense, that is where exist generic and homogeneous solutions sufficiently close to the solutions, then indeed it can be easily shown by using this Lagrange procedure where it should exist with modes. Okay, what do we actually have from observation? This is the temperature of CMB anisotropy. I use here a rather old method, but it is sufficient for the aim which I shall present in the next slide. Okay, and what in the statement is, as I said, that these from the observational point of view, two-parametric mode are sufficient to explain this curve, both in anisotropy and polarization. There exist some features here for multiples you see from L 20 to 40, some possibly 10% corrections, and I shall discuss it in the end of my talk in connection with our some recent paper. But note in particular that in polarization up to here at L 30 to 20, we don't see some such significant deviations, and it will be important. Okay, and so all this is pictures, but all this can be concentrated into two numbers from the observational point of view. From cosmology, we have two numbers, which from our present understanding are a kind of new fundamental parameters of nature about the amplitude and the slope. We have by the fact that we have two small constants means that we can use two kinds of perturbation theory. The first with respect to this parameter, so consider perturbation as small, and using this small parameter, it's not so small, but so sufficiently small. We can use what is called the slow expansion in the slow parameters. Okay, this is from observations. From the theory, the statement is that in the simplest models we can predict and derive the second constant, and omitting more complicated 10% corrections were predicted in the simplest models is simply that this quantity by models multiplied by this constant, which has nothing to do with the early universe. It's simply because it's constructed from the present cosmic background temperature and the Hubble constant. So okay, this multiplied by this is approximately 2. So once more, that you can see it without complicated computer program, the transfer is a program that it is really show. Let me also, as I said, R is not measured, so let me just mention the most recent upper limit on the quantity R, from which, by the way, it makes all the so-called chaotic inflationary models described by observational data. So, okay, now let me very shortly present you this one parametric models which produce the correct value for ns-1, and this is my original R plus R squared model. The same prediction for the scalar field mode with the asymptotically Higgs-like potential and strong non-minimal coupling. So it's not simply Higgs, it's strongly non-minimally coupled. I shall show you how exactly. First, it was considered by Pohang, but identification of this non-minimally coupled scalar field by the Higgs was proposed by Bezukov and Shaposhnikov. And what I want to emphasize here that actually the prediction of these models are actually the same. So speaking not at the phenomenological level, it's actually the same model. And the reason is, though this model is often considered as a particular case of so-called for the gravity, it also can be considered as approximate. These first models can be also considered as approximate description of a second model without any conformal transformation. And this follows simply from the fact that for inflationary solution in these models, it appears that we have what can be called the geometrization of a scalar, that is the scalar field algebraically follow the behavior of a richer scalar. And that's why we may, not for all solutions, but for inflationary solutions, we may even make the thing which is not usually possible. We may substitute the solution into the action itself, and then it appears that non-minimally, strongly non-minimally coupled with this potential just reduces to the R plus R squared. And so R squared inflation solves the intermediate dynamical attack for a large class of scalar tensor model. And also it appears that we find out that uses the third effective one parametric inflationary models, the combined models. And the reason is that just using this effect of geometrization of a scalar during inflation is just refers to these models, but simply that renormalized this scalar mass. Okay, and now just let me go to the next. As I promised you, you can see how that homogeneity, once more, of course, according to these inflationary models. Okay, once more, looking already at this picture by bare eyes, you may see how that homogeneous should be inflation. And that's why it follows from the relation that actually in inflationary models, the origin of there exists original source are quantum perturbations of some scalar degree of effective scalar degree of freedom, but how they are translated into the scalar into present scalar perturbation. And actually, the origin is purely kinematic, and this can be summarized. It's that in these models, slow roll models, inflationary stage had a little was slightly duration of the stage was slightly different in different points of space, and so the quantity R, the cultured perturbation, is what is simply the difference in the number of e-faults. That's why now, okay, I shall finish in 5 minutes. Okay, and so just now, and though the real exact relation between perturbations and delta T over T is very complicated and require a very complicated computer program. In this region, scales exceeding 1 degree, the relation is very simple, and so it's simply delta T over T is -1/5 of R, and according to the delta N formula is -1/5 of delta N over N. And so returning to this picture, because I want to emphasize, because usually going to power, sun is emitted. So according to inflationary stage, large oceans here corresponds to the places where inflationary stage was a little bit longer. It's just the opposite. Large mountains regions corresponds to the place where inflation was a little bit shorter. How much shorter? In terms of E-folds, just using this expression, you may immediately obtain that the observed difference in the number of E-folds is of this kind. And if we take the simplest inflationary models in which no small or large parameters which do not follow from observations we introduce, then the statement is that we really see time differences, only one order of magnitude exceeding the long time. You can say how is possible to make any serious statements about Planck time difference? Because we refer to macroscopic scales of the order of 1 meter at the end of inflation. It's just for the same reason that we from gravitational wave observations, we measure shifts between mirrors of the order of 10 and minus 18 centimeters, much less than the size of opponents. And we don't need to think about extensions of the standard models to the energies of 10 to the power 5G. We just, for the same reason, it's possible really to say that this averaged over large scale shift really exist. Okay, and still, it's well possible to expect some deviations. And one of the simplest way, actually, based on my paper, is to have some features in the influence potential. The origin is due to interaction with some other fields experiencing the fast phase transition during inflation, and in particular, just I obtained this exact solutions for this very simplified models. But of course, it can be generalized, and here are different generalization of these models. The exact solution which I showed in the previous slide corresponds to this curve. Okay, and what I want to say at the end of my talk is just to refer to our recent paper with my collaborators, including in particular the next speaker, Professor Smoot, and we really compare it with a large class of this possible deviations from the exactly scale-free spectrum. We have observational data that using the most recent temperature and observation data, and once more, I don't have time to go into more detail, but the general result why we really see some features looking at temperature anisotropy when we add polarization that these features becomes not statistically significant. And compared with other paper, it seems that this is the general lesson you should be taken into account. And once more, one should look not only at simply temperature, one should look at the polarization too. And finally, a very short remark. Still, let me, as a very possible, very exotic possibility that still, though it seems in CMB fluctuations, we don't see any very unusual effects. Still, there may be some hidden information. An example, for example, was our search in this paper, and actually in the previous paper, for some additional component which has exact mirror symmetry. Okay, so the present situation that we don't see such statistically significant effect, but once more, it cannot be excluded that there are some hidden, still there are some hidden informations. Okay, so that's why my conclusions, modern cosmology does not require the cosmological principle. It's the principle assumed before the consideration of concrete models, where simple viable inflationary models, they produce the predictions for ns-1 confoundable observation and the target prediction, not only possible, of course, but the target prediction for the R, where the actual, of course, for this, depending on the post-inflationary stage, the actual that values are slightly different. The duration of the inflationary state is almost the same in different spatial points. So we can really say that, of course, in the scope of the inflationary scenario, inflationary stage in the past, the difference in the duration of state in the past were averaged on a little bit, only a little bit larger than the Planck time. And as I said, for non-scale features, though the present temperature and polarization data do not favor them, we're not able to exclude them completely. And finally, for some, I would say, fantastic possibility, actually inspired by the Carl Sagan in novel contact, that there may be some master signature hidden, deeply hidden in the sea, in the U fluctuation, though of course it is strongly bounded by the upper level of Christianity. Thank you.
Yeah, thank you, Alexei, for your insightful talk. May I combine all questions to your talk into discussion? We have discussion session.
Okay, okay.
Though I'm the chair of this session, I have to drive back home to join evening colloquium by George. So may I yield my chairmanship to Elwin or Stephen? Stephen or Elwin, do you hear me?
Yeah, I can hear you.
I have to prepare my trip back home institute, yeah.
Okay, yeah, we can do that. Owen, are you here?
Yeah.
Okay. Okay, I can do that. Yeah, no problem. So.
And so, and when the discussion section begins.
Okay, so the discussion session is now. So if you have any questions to any of the speakers, then please raise your hands. So it can be to any of the speakers from this morning session or the afternoon. I think some of the morning session is still here too. So you can also ask a question in chat. So we have one question in chat to Professor Starobinsky. So what is the reheating setup for Starobinsky model of inflation?
Okay, it's a good question, because actually the reheating setup is some additional. So it's the next part after inflation. And so, as I said, formally that we have the same predictions in both R plus R squared, or Starobinsky model, in the Higgs model, and even in the mixed model, the actual value of this capital N as a function of a present scale is slightly different, depending on our assumption of how these inflatons in these models, in our model, I call it scalar, how they are coupled to usual particles. And so that's why the simplest variant, which is usually considered, is that if you don't introduce any new mechanism for reheating, but simply use just the same mechanism which was used to produce netic perturbations at large scales we use just the same mechanism to produce the decay of the effective scalar particles, it's called scalaron in my models, into any pairs of particles, antiparticles of a fusion matter. So it is essentially the same effect, the creation of particles and field of fluctuations in the external gravitational field. And the difference in this value of capital N, which I mentioned, between these three models is simply due to the following. The simplest variant is we consider only minimally coupled usual field. In particular, the most effective decay of a scalar is two minimally coupled scalars. But in the Higgs inflation, in the mixed R squared, these scalar particles is assumed to be Higgs and Higgs inflation is actually strongly non-minimally coupled, and this enhance the effect of particle accretion much. So though the post-inflationary stage in the Higgs model and the mixed R squared Higgs model is much more complicated than in my model, and there exist many subtle and interesting, I would say, almost stochastic effects. The main difference between these models is just the difference in the assumptions that either the main decay channel is to minimally coupled scalar particles or to strongly non-minimally coupled. And this taken into account this characteristic coupling psi, which I mentioned shortly in one of my slides, which of the order of 4,000. This results in the shifts of the n corresponding to the pivot scale, the 0.05 megaparsecs, approximately by 4, approximately from 58 to 54. Okay.
Okay, thank you. Thank you. So we have, so I'm going to ask Christoph Solder. You have a question?
Question for Konstantinos. And my question is, for your galaxy, cluster scaling relations, do you consider any evolution of the galaxy clusters? Because I think that will be a big effect.
Right, yes, we do actually. So the evolution of scaling relations is quite well known by now. So we do account for that. However, it's not important for our samples, because this cluster evolution starts to become important after redshift 0.15 or so, where our focus, the focal point of our work is below that redshift. So even if we do or do not account for any evolution, one would get the same results. Now, if we go to higher redshift clusters, then we do have to account for this evolution, as we do already. But again, if the redshift distributions of different sky regions are similar, then if one doesn't correct for this evolution, the bias would be cancel out, let's say, for different cluster populations, since it will be the same towards one direction and the other. So that's a problem, and that should be taken care of only if one is using high redshift clusters, and if the redshift distributions of different sky regions are very different. So it's irrelevant for our work, but it's important to note for future work with higher redshift clusters.
Okay, thank you.
Okay, thank you. So Dominic and then Misa. So Dominic.
Yeah. Hi, Alexei. I would like to ask you whether you think it would still be useful to say that the cosmological inflation kind of predicts something like a cosmological principle, but not in the form that it says the universe has an exact symmetry, but that it makes a statement on the statistical properties of the universe.
Indeed, yes, I agree with this. So indeed, so indeed, in unfortunately, in models approximate cosmological principle is a consequences. Of course, once more, not for all solutions, but where, as I said, there exists generic class of solutions. Once more, are according to the terminology of general relativity. Generic means solutions which have a non-zero measure in the space of all initial conditions. So that's where exists generic in the simplest. Once more, I would say in the simplest inflationary models, where exist generic solutions which indeed predict approximate cosmological approximate the homogeneity of and isotropy of the universe at the present time. But at once more, from the general point of view, not to arbitrary large scales.
Sure, thanks.
Okay, thanks. Ms. Al.
Yeah, thank you. So this is a question for Chethan. So you have this modeling of this anisotropy or flow or whatever you call the parameter beta, right?
Yeah.
Yeah. So how is it determined? Is it the free function, or it's determined by some initial condition, or maybe the equation?
Yeah, I think it'll have to be an initial condition. Yes.
Initial condition.
Yeah.
So can it, for example, okay, so it does not depend on the equation of state much, or let's say, as we have you heard that at the redshift of about 1000, perhaps the anisotropy or inhomogeneity, whatever it is very small. Yes, on that scale, 10 to the minus 5 or so.
Yeah.
So if you start with that initial condition, can you increase that to the level you're talking about?
So the zero thought answer is that we have not really explored its evolution. But the thing is, they're all ODEs, so in principle we can try doing that. So I think your question is basically, why is it that this quantity is somehow remains small? Or it starts out very small, but evolves and stays small.
Yeah, no, it's the other way around. Usually, in the anisotropic universe models, whenever the anisotropy you have, it usually decays out. It's very difficult to keep the anisotropy.
Right.
Yeah. So this means if you need some ingredients.
So the only answer I have is one of the things that I mentioned in the talk, which is that it couples to the it basically the curvature parameter couples to this, is in the sense that if you set the curvature parameter to 0, a natural way in which you can make it vanish, if you set the curvature, the A naught that I had in this equation is 0.
I know, but the curvature parameter again is it's just a parameter, and the spatial curvature, if the universe overall expands, unless one direction is contracting, the curvature decreases. So effect of curvature decreases, and which means that the beta generally should decrease, right?
Right.
So that's my question. Or so if
right. So at the level, I think the level is which you're talking about, the anisotropy is decaying can be made at the level of a statement. So so essentially the answer to the zero thought answer, as I said, I don't know the answer, because the point being that we don't know whether these solutions of these things are stable.
The point is that it seems it's more reasonable to just start from, say, standard sort of isotropical homogeneous universe, but they include some inhomogeneity.
The question of stability of your question can be translated to a stability of solutions of this in this.
Yeah. What I mean is that usually as soon as you assume the homogeneity, any anisotropy decays out. But if you include inhomogeneity, then the anisotropy can grow.
It's not an inhomogeneity. It's more like it's an anisotropy. So
no. So my point is that I don't really know any mechanism without inhomogeneity to increase isotropy in time.
I agree with you, and I think that, but our intuition is largely built on FLRW and its perturbation. So I think that it will be good to investigate these equations, especially because they are simple ODEs, as dynamical systems, and see what their phase space looks like, so that we know what kind of attractors, etc., exist there. So I think that I agree with you that if you just take FLRW and it stays order one, it stays close to that. And if you can really see it as just a perturbation of that, probably it is not a very interesting thing. I mean, I say, I don't want to oversell it at all, but the point is, I think that we have two extra variables, and I think it is probably worth looking at what the phase space of this full system looks like before, seeing whether it is,
but perhaps you can just guess from the equations you have, huh? I mean, it's
right. But we have had those equations only for like about 1 or 2 weeks, so we haven't really looked at them in detail.
Anyway, thank you.
Yeah, sorry.
So may I make a comment on the discussion we just had?
Yeah, sure.
So I think Misau's concern, which is I think a very rightful one, is how this. Let's suppose that late universe we have this tilted model that you presented, whether it could be connected through cosmic evolution to something reasonable in the early universe. That's another way of putting Misau's question, if I understood it correctly. And yes, the point was basically the anisotropy decays of like 1 over scale factor to power 6. Yeah. So in order to have any reasonable, sizable anisotropy in the late universe, we needed to start with a huge anisotropy in the early universe. And we know that
that's not the case. Yeah.
There is no data supporting anything like this. So basically the question is whether this late universe could be connected to anything reasonable in the early universe.
Yeah. No, I understood the question. I think, but my answer to that stays. Right? The basic answer is that we don't have a real understanding of the phase space of this thing at all. So I don't, if it is too closely connected to FLRW, I don't think it is going to be, FLRW means, lambda CDM. I'm not very sure that it will change the setup, I think it is kind of related to the Dominic's question also. So if it is, if it can be viewed as a perturbation in some small way, probably it is not very interesting. So,
okay.
I think the key point is that if lambda, so one of the things I mentioned in the chat is that if you can, I have this sort of this wild hope that maybe cosmological constant itself can be gotten rid of by doing something along these lines. So in which case you would be in a completely different branch of solutions. It won't be perturbatively close to lambda CDM. So that of course is, it's just the equations are very fresh. So I don't really have much to say about it, but I do think that it is, there could be many basins in the dynamical system that we see for these solutions. So it need not just be in the vicinity of the lambda CDM solution. So yeah.
Okay. Thank you, Chethan. So we have questions from Jenny, and then George, and then 2 from the attendees. So Jenny.
Thanks a lot. I've got a question for Konstantinos. When you determine the temperature of your X-ray galaxy cluster profile, then you need to evaluate the spectra. Do you introduce a cosmological model through the back door? So which influence does the cosmological model for the spectrum evaluation has on your temperature? Because all your graphs depended on the temperature.
That's an excellent question, thanks. So yes and no. So yes, in the sense that one has to select the region from where the spectrum is extracted. This is done based on the characteristic radius of galaxy clusters, R500, in order to be consistent and measure the temperature within the same region for every galaxy cluster dynamically. So now this R500, in order to be evaluated, it goes through some weak cosmological processing, let's say. So one observes how luminous a cluster looks like, and then takes a scaling relation with the mass, determines the mass, or with other methods, maybe weak lensing measurements. And from the mass, you can determine the R500. Now, however, it happens so that what we care about is actually the apparent size of R500 in arc minutes and not its physical size in order to extract the spectrum. So when H0 is changing, two things are happening at the same time. One is that the initial luminosity that was used to evaluate this radius increases or decreases because it depends on H0. So the mass is changing, the estimated mass, and the estimated R500. At the same time, though, the apparent R500 is actually the physical one which is changing over the angular diameter distance. The angular diameter distance also changes when H0 changes. So at the end, the apparent angular radius that we use to extract the spectrum is nearly completely independent of H0. Actually, it depends on H0 in the power of 0.076. So it's pretty standard then that if we use an H0 of 40 or of 90, we'll extract the same spectrum from the cluster without worrying about H0 variation. Now, it becomes a little bit more tricky if omega matter is changing. Then the spectrum, let's say, from which we extract the temperature, it might change more strongly than H0. However, we do not care about omega matter in our work because we are at lower redshifts. So we care only about H0, and this has no effect in the temperature at the end.
Okay, thanks a lot. So you do not have any degeneracies between H0 and omega matter at this point?
So not really, because omega matter doesn't really affect the distances up to 0.1 or so, or 0.15 that we are using. The effect is minimal. So H0 has a many times stronger effect than omega matter.
Thanks a lot.
Thank you. Thanks. So, George? Maybe George has decided not to. George Smoot, your hand is up.
Yes, sorry, I had to unmute. I had a comment. I raised my hand originally because I had a comment in addition to what Alexei had been saying. And a few years ago, 3 or 4, I don't remember, maybe longer, there was a commemorative of the 50th or 70th or something anniversary of the standard model. And I gave a talk, and in that they're talking about the various models we're going, but I gave a talk in which I gave an example of how the cosmological principle was actually a dynamical symmetry and not a true symmetry. So there's a distinction made in fundamental physics between absolute symmetries and dynamical symmetries. And if you think about you're going to have space-time appear or gravity appear as emergent phenomena, they're not fundamental in their principles. They emerge as a result of the dynamics of what's going on. In the case that we're talking about, in which you have inflation as the original driver of space-time, you then can make a prediction based on the number of e-folds that you think you have, which is more than 50 and less than 75 or something like that. You can make a prediction of how well behaved you should get a cosmological principle. And if you assume the potential is very flat, the way Alexei's model does, then you get a well behaved. If you put extra kinks and bumps in it, then you can get extra phenomena. But you can predict with a simple version how well the cosmological principle should hold on these different scales. And you can test that by these observations. And you don't expect it to be perfect, but you expect it to be quite good given the number of e-folds. And that's exactly the thing that Alexei was saying is thing. And then this is a reflection of the symmetry of the driving, vacuum that you have, or the model that you have, which is, you know, bunch Davies or whatever vacuum you start from. There, you're depending on the isotropy and then the homogeneity, because you could make things vary across space. But the isotropy is an extremely well-tested phenomena, both locally and at reasonable cosmological distances. So it's only inhomogeneity you could put in by hand or something. Anyway, that's more than I wanted to say.
Thank you, George. Thanks. Any comment on that? If not, we've got some. Oh, Shane, sorry.
Yeah, actually, I wanted to add something on George's comment. I shared the paper actually that we wrote in 2012, and this is an extension of the famous cosmic no-hair theorem by Wald. And we have extended this to inflationary backgrounds. And actually, we have shown how much room inflation leaves for having anisotropy. For slow roll, inflation is less than 1%. But the details could be found in the paper that I just shared.
Thanks, Shane. There's a bit of an argument forming in the chat. So, Subir, do you want to comment?
Yeah, I just wanted to say that I think there was a claim that you could formulate a no-hair theorem for inflation, but I think it was shown fairly rigorously by Vachaspati and Trodden using the Raychaudhuri equations that you need a initial patch at least 3 times as large as the Hubble radius in order to initiate inflation. And therefore, effectively, inflation assumes an FLRW background to start off. And therefore, you know, from an ontological point of view, you cannot say that it would ever predict FLRW. But we all know the difference between almost theorems and you know, rigorous theorems. So these are all folklore in a way. What is important is that we are focusing in this meeting, I thought, on what we actually observe in the sky, not on theoretical ideas about what might have happened in the very early universe. So I don't have more to say.
Sure. So since the comment was made, I just wanted to add onto this. You're of course right.
Thanks.
Stephen, may I ask a question?
Yeah, please.
Yeah, so this is in a way like, so from the talks that just happened, so there are these 2 directions which are emerging, which is the bulk flow towards the, there is a direction towards the dipole. There is some discrepancy either in amplitude or some of the directions pointing towards that, and we will be having a talk by Enjoy and others later on. We will talk about the direction, and the other one is something that was that Konstantinos also discussed, which seems to appear, which actually goes in the direction of the hemispherical power asymmetry in CMB. So, and to my understanding, this seems to be the usual in the multipole decomposition, that L equal to 1 mode, if we were to say, and that hemispherical power asymmetry is something that is that is extracted from multipoles beyond L equal to, from L equal to 2 and more, perhaps on larger scales up to 60. So how do you understand these 2 different directions? I mean, this is just not, it's something that I am thinking, so I'm just saying it loud. It's not just for any specific person or something. And then specifically to Chethan, so in the model that he considered, so if you just take A not equal to 0, that just boils down to the Bianchi 1 model with residual axial symmetry, right?
Yeah, I think so. Yeah.
Yeah. So A not equal to 0 if you take. So even in that model, we had analyzed supernova data with residual SN1A and assuming domain walls cosmic strings, etc. So all those directions somehow come out to be again in the hemispherical power asymmetry direction. I will give the reference in the chat, but so there are these two different directions that I see in from whatever happened, and of course, and I believe it is going to emerge more strongly with the presentations that are going to come up. So that everybody that how to think about these things. Just one open question.
Yeah.
Just
Okay, thanks. So we have, who wants to have any other people? Professor Starobinsky?
Okay, thank you. So I first want to answer the old question by Subir, and then a comment to his later remark about, in particular, about Wald theorem and so on, and that inflation, in fact, inflation do have hairs, and moreover, not only inflation have hairs, but that these hairs are actually absorbed. These hairs are actually absorbed in C and B. Is fluctuation, then Chuck Smoot was the first person who observed them. And so once more, I think that there is a, though I shall refer to my old paper that I written at the same year as the old paper, I think there still exists some confusion, because old paper assumed homogeneity. So in case of inhomogeneity, whereas the generic. So let's first speak about speaking about the first Subir's questions. The key word which was absent in this question was slow roll inflation, or better to say inflation with a metastable cosmological constant. So let's first remind you that theorem about the generic behavior of solutions of the general relativity with exact cosmological constant. The general statement is the appearance of locally Friedman-Robertson Robertson solution is a generic property, so it's natural to have late time asymptotics which are locally isotropic, but they are globally inhomogeneities, and the generic solution, generic late time asymptotic. Once more, I remind you that generic does not mean general. It does not mean that all solutions that have this behavior. It means only that there exist solutions with a non-zero measure in the space of initial conditions, which has this behavior. So once more, in the case of exact cosmological constant, the appearance of local isotropy is natural. And actually, it was known even 60 years ago when people discussed why the present state of the universe is isotropic. The only difference is that they think about cosmological constant, which is now, and do not think about possibility of large cosmological constant. So okay, so no problem in case of exact cosmological constant. But the main problem of all inflationary models is not how to begin inflation; it's how to end it safely. And that's why we really need metastable, so slowly decaying, and then this exact asymptotic behavior becomes an intermediate attractor. And so indeed there should be some conditions, okay, in terms of the effective potential, it should be sufficiently flat. Well, once more, sufficiently close to the cosmological constant. But once more, if it is indeed metastable, and I agree that, of course, it's a strong assumption, but okay, it can be tested by observations. Then it's possible from this exact late time, exact attractor at late times, it's possible to obtain intermediate, to use them as intermediate attractor. And so once more, inflation do have hairs, and actually even not in inflation. Once more, even solutions of general relativity with an exact cosmological constant, they do have hairs. It's another questions that for the exact cosmological constants, these hairs are outside the event horizon of one observer, but I did not agree with those people who say that we can discuss only what one observer can see. It is certainly not so. So once more, because the world theory assumes homogeneous behavior, it's not applicable to the real inflationary model. So inflation do have hairs, and both scalar hairs and tensor hairs. Scalar hairs are already discovered, and partly, of course, partly in the sense of scales. And what we expect now is to find tensor hair. Okay, and then I was make another remark, actually unrelated remark regarding, I think, the question by remark by Mr. Sasaki. Okay, so as far as I understand, his question was how to obtain some, let's say, non-trivial perturbations at late times. Of course, it's not possible in the standard model. In the standard model, assuming cosmological constant and say radiation matter and so on. But as I mentioned, if it would appear, suppose it would appear that indeed dark energy density grows with time, this will be a kind of some instability, and it's well. So this instability, the reason of this instability will be existence of some unstable modes, and then I would say that once more, would it be really discovered, then I think it would be rather natural that then we also have some growing, some kind of isochirality of modes which will induct energy which will grow with time.
Can I just add a comment to that? Alexei, everything you said is of course correct, but there is a additional remark one could make when discussing things at the quantum rather than the classical level, as you have been doing. And Jia Dwali and collaborators have been of late emphasizing that in any quantum theory of gravity, requiring the S matrix, the most fundamental object we have for studying scattering processes in quantum physics. As you know, de Sitter space does not have a compact future horizon. You cannot define initial and outgoing states on that. And therefore, they argue that a constant, cosmological constant, is in fact ruled out by considerations of the S matrix for a consistent theory of quantum gravity. You could, however, in principle have a potential with a tilt, as you said, something that has a arrow of time. And indeed, they work out the so-called lapse time, how long such a situation could last in order to be consistent with the S matrix. Now, these are all preliminary ideas, but this is exactly what leads to this notion of the swampland in the landscape of string vacua. And but as you know, there are people very interested in that concept and working on it, and I'm sure we will learn a little more about the plausibility of a cosmological constant per se, and of vacuum energy that actually has a potential with a tilt, which currently appears to be more consistent with such ideas than a constant cosmological constant. Thanks. That's all I wanted to say.
Okay. In turn, Subir, may I add? Of course, once more. But in fact, I spoke mainly in my comment to the Mr. Sasaki equations. I spoke not about the problems of quantum field theory. I spoke about possible properties of a Present-Dark energy. So I would say that's why I would say, independent of any arguments from the quantum field theory, if once more, if it will be found that the Present-Dark energy density grows with time, okay, it will be really very unexpected that phenomenon. First, and my second unrelated remark, which actually, indeed, you mentioned asthmatics, and indeed it's a general question also to you as an expert in this field. What do you actually mean by asthmatics? Does this mean that it's asthmatics which describes all process by one observer? If it's so, I have doubts if this is so because the statement that we can in quantum theory, but of course also in its classical level, that we can say that we can speak only about things seen by one observer, I would say it's very restrictive. In particular, speaking about usual gravity, this was the result in the statement that we really see many black holes in our universe, but when from the point of one observer, why one cannot discuss interior of more than one black holes, because one observer cannot go into interior of two black holes. I would say that by now nobody said that it's not possible what happened to discuss what happens inside black holes, but this requires more than one observer.
Well, I take your point. I'm not qualified to comment on it. This really ought to be addressed by the authors that I was referring to, that is Dipole and Cesar Gomez, who have written a series of papers on this. I'm pasting one of them in the chat box for people to look up.
Yes.
Yeah, but I take your point. Thank you.
That's great. Thank you. We have Dominic.
Yeah, I would have a question just to change gears a bit to Kostas. Namely, the question is, how do you determine the redshifts of your clusters? I mean, is this done from the SZ effect, or do you use the galaxy redshift measurements, or how do you find out whether you, I mean, what effect does this have on your accuracy, on how well you can measure H0?
So the redshift for 80% of the sample or 85% of the sample is measured based on a spectroscopical redshifts from the galaxy members of each cluster. So we only consider redshifts that are evaluated based on at least 10 spectroscopic redshifts from galaxy members. For the clusters that we have fewer than 10 spectroscopic optical redshifts, we actually measure the redshift from the X-ray spectroscopy of clusters, so simultaneous with the temperature. So there is this very strong iron line at 6 keV from the clusters that can be used together with other emission lines to determine the redshift. The redshift uncertainty that we have for both from the spectroscopic galaxies, the scatter of these redshifts within a cluster, and the X-ray spectroscopy is propagated to the cluster properties, such as the X-ray luminosity.
Okay, could there be a bias from for instance, if you get spectroscopic redshifts, maybe could it be that it's more likely to get some redshifts from objects that are in front of the cluster rather than in the back of the cluster from our line of sight and things like this?
Mm-hmm. So when we actually determine these spectroscopic redshifts optically, we take the full catalogs within the field of view of clusters, and we can easily separate the foreground and background galaxies from the cluster by just doing a 2 sigma clipping. For the X-ray redshifts, this is not very likely because projection effects are not that strong in X-rays. One can easily tell if there is a foreground or background cluster emitting X-rays within the same field of view. And it's also shown in the fit of the spectra. Now, if there was such a bias, I think it would be very hard for such a bias to exist, but if there was such a bias, it would be very surprising to be so directionally dependent. Just, have many projection foreground effects, let's say, for one region of the sky, and many background effects for the other region of the sky. But this is a valid point, and that's why we actually devote a lot of time into making sure there are no projection effects in our sample.
Thanks.
Okay, thanks everybody. Any more questions from the panelists?
Actually, because we're on it, Dominic, did you ask your question or my question to Kostas about the wavelengths, right?
No, maybe you ask it.
I'll ask it. So Dominic seems to have, if you look at Dominic's paper from 2020, there seems to be some frequency dependence in the dipole, in the cosmic dipole that he infers from radio galaxies. Do you see any of this in your sample? Because you were discussing wavelengths at some point, right?
Yes, exactly. So we see the same direction and the similar amplitude of the dipole across X-ray, microwave, and infrared. Now, of course, some variations exist. For example, in the X-ray luminosity temperature relation, we see a dipole at a 9% level. On the microwave Y-Z temperature relation, we see it at a 14% level. So these random fluctuations are expected to exist. We haven't thought of the possibility that the actual background cosmological anisotropy that we are investigating does depend on the wavelength. But I would be, at least from our sample locally, I would be surprised if these small differences are due to some physical reason rather than just noise or sample related issues.
Right, thanks.
If I could just add to that, the frequency dependence in the radio that Dominic and collaborators drew attention to is largely driven by the analysis of the TGSS survey, which was done from the GMRT in Pune, and that had significant systematics. We have in fact been doing a reanalysis of the TGSS data, and we do not find that you can confidently say that you get a different dipole from that survey as compared to the other radio surveys. So I'm skeptical that there is any frequency dependence of the measured dipole. This is consistent with what Kostas said. Okay, great, thanks.
Yeah, we can discuss this tomorrow.
Yeah. But do you agree that the signal the indication of frequency dependence is driven largely by the TGSS analysis, right? You agree with that?
Sure, it's the strongest hint
Right,
towards that.
right.
I agree with that.
So that, yeah, so we need to look at it a bit more carefully, as I'm sure
we
you're
have to
doing.
understand whether we can really explain the TGSS signal with something else than being on the sky. That's true. Yeah.
Great. Yeah. Thank you.
Yeah, thanks.
Dominic, you had a question for me that you could not ask after my talk. Did you?
Yes. What I wanted to comment or more or less comment and question maybe is I mean, you when in the thing how you treated the supernova when you fitted this deceleration dipole, right? You fitted a dipole in deceleration parameter, but you did not allow for an arbitrary velocity, so to say, of the observer, right?
Correct.
So we recently did a reanalysis of the Pantheon data set, but not as it comes on the GitHub of Skornik, but an improved one, which was compiled by Charles Steinhardt, who corrected all kinds of mistakes that were made in the redshift transformation from heliocentric to CMB redshifts. We further found a few mistakes in supernova positions that were in the data set. We also fixed that. And then we redid a fit to the Pantheon, to this corrected Pantheon data set, where we say we vary all cosmological parameters that are relevant of the lambda-Kotak meta model. Plus, we don't assume that we know the CMB frame. We leave this as an open parameter. Yeah, so we kind of fit for the proper motion of the sun with help of supernova data. And then we find something which is actually a very nice fit of the lambda-Kotak meta model, but we also find the CMB dipole direction, but we find a velocity that is actually smaller than the CMB velocity, which is actually consistent with the claims about the bulk flows, because the bulk flows point to the opposite direction than the CMB dipole. If I have time,
the bulk flow is it's in the same direction, surely. I mean, roughly, it's about 30 degrees off, but roughly
it's the same. But I think it counteracts the CMB motion, right? The bulk flow.
Yeah. My comment about Pantheon, actually, Mohammed Ramiz is online. He might want to say this, but we looked at that pretty carefully, as you know, and pointed out these anomalies that Charles Steinhardt also independently found, some of them. The thing is that the data set, as it is made publicly available, does not include all the necessary covariances. There are several sources of uncertainty, and for each of them, the covariance needs to be stated separately. Otherwise, you cannot undo them separately and check the consistency of the catalog. Unfortunately, they have not done this, as you know. This was only done by JLA, and no one after them has done it. And this makes it very difficult to do open science. That is to say, I could always approach somebody and get a version of the Pantheon catalog, but that is not public. That does not have a record of the changes made to the catalog. It really needs to be all done in a public forum like GitHub, so that people can see what changes.
I fully agree with you. I was actually shocked by the lack of provenance, curation of the data. Right? It's not the.
But unfortunately, it's all the responsibility of Dan Skolnick to do all this and make all these corrections. And poor chap has had to carry the burden of this. But my point is simply this, that if people want their results to be assessed by others and checked, which is something that we would all surely want to do, in the spirit of open science, then we should make our data and codes publicly available on a website with a tracking mechanism like GitHub or Zenodo or whatever, and then we all know we are on the same page. The reason I mentioned this is because I was particularly upset when Adam Rees said in some interview to Physics World that we were using a catalog, the joint light curve analysis catalog, which was old, and there are newer catalogs with more data, and that is why our finding of the anisotropy was suspect. Now, I would be delighted to analyze a catalog with more data if they would only make it available with all the necessary details, and you know that, right? So I really think that this is something that the community should push for, not accept the idea that this data, which is of crucial importance for cosmological analysis, should be kept in somebody's private repository and altered as they feel like. Just as with Planck data and WMAP data and ROSAT data and other large astronomical data sets, they should be made available publicly. Sorry, rant over. I just was rather annoyed by that absence of publicly available data, because otherwise we cannot, maintain standards. Yeah, thanks.
Okay, thanks, everybody. I have a question if there's anyone CMB related here. Is the Planck and WMAP data before the dipole subtraction, is that available publicly? Because I had a quick look and I couldn't find it. Does anybody know?
I guess you can get the time ordered data and then redo everything yourself, but this is very
tedious. It's painstaking. It's very tedious. Yeah, you're right. That is done as a standard before it is made public. But well, at least there you know what correction is. Well, how shall I put it? You have to appreciate that these modern experiments are so complicated that to analyze the data requires assuming a framework, and that analysis is carried out in that framework. So Planck, all these beautiful power spectra that people show, that results in the end after a lot of work. You start from the raw sky maps, you have to correct for apodization, you have to do de-striping, you have to do smoothing, you have to compensate for all the pixels that were damaged by cosmic rays by interpolating between them. And most people never look at those papers where the collaboration, it describes in detail all the things that they had to do in order to actually make a sky map. And perhaps people should, because then they would have a better perspective on how much effort A goes into making those maps, and B, the fact that it necessarily requires assuming a framework, typically the same framework that is then presented as the answer, the lambda CDM with primordial perturbations which have a small tilt. That is what is assumed. So unfortunately, this is unavoidable because of the complexity of the problem. Dominic, I wonder if you would agree with that.
Dominic just had to drop out, I think so.
Yeah, okay. Anyway, he has faced the same issues, but most people don't look at the actual data or try to analyze it. They go by what is presented as the final data product. But when we are asking questions which go back to the sort of foundations, then we do need to look at the data for ourselves. And I'm just making an appeal that all such data should be made publicly available, including all the detailed covariances, without which you cannot do a principled statistical analysis.
So I mean, my comment was similar. So in the sense that it would be nice if the whole analysis pipeline for Planck was available publicly, so you could run the time order data through their pipeline and then see step by step, because like you said, to do it yourself from scratch is a painstaking process. So it'd be nice if the tools were available. But
yes, well, I mean, it's actually part of the public charter of experiments like Planck or WMAP, which are funded by the agencies that fund them have actually committed to that. That is why Planck was required to make all the, as you know, the data products and tools available online within a certain period. But of course, as we all also know, it's very hard to keep deadlines when you are actually struggling with such a huge task, and people don't always manage to make it on time. But I think the principle should be respected. All the data should be made available.
Okay, thanks. Maurice, so we're going to have to wrap up soon, I think, so we're running out of time. But Maurice, do you have a question or comment?
Yeah, I have a short, well, basically amplifying what Subir just mentioned in his comments. He wrote briefly, although it's not a central topic of this meeting, that the signature itself may be, unstable. And I think this is a point we in the last few years have been looking at, and in some sense, we feel it has been under-highlighted as a potentially important ingredient, especially also in late-time cosmology, as it may, for instance, indicate that there is despite the fact that this sounds anomalous, there may in fact be a turning point as a result of that in H of Z. So I think this issue deserves perhaps a lot of attention, more so than so far has been given, also in the context of data analysis of late time expansion. And then I have a question, actually also following up on the points that he is raising right now, and maybe I can address this also to George Smoot. What would be, many of us have this issue of, do we have access to the data? And since George has been, of course, a member of a large collaboration, in this case on the CMB, maybe he can give a comment as to what is a procedurally reasonable diplomatic avenue to entice large experiments. And I'm thinking much broader, CMB, but also things like gravitational wave data and so forth, just more generally, to adhere more to the NASA standards that ultimately the data should be public. Is George still there?
I have to unmute.
Okay, yeah.
All right. So I have been thinking about this for other reasons, and actually in less than a week, I'm giving a little talk about this kind of stuff, but it's in a different vein. But for the COBE DMR, I had read the NAVSTR standards, but I also believe myself that we would be better off releasing the data as early as we could and as completely as we could, because more people could then analyze the data, more people would be paying attention to the data. And that's what turned out, that very much did. Now that was over the objections of some of the team members, and particularly the people who are actually working. The hardship was on the people who were actually working on processing data, because we had 4 years worth of data, and yet at the end of the first year, released the first year data. And if you're busy working on the pipeline and getting the calibrations and improving things, you don't have as much time to write scientific papers. And so it is a hardship for the people who are writing papers, but the return that you get is that you get much more attention to your results and much more belief in what's going on, and people's interest in it when you go public. Now, when it came to WMAP and then particularly Planck, there were tensions in the situation, because there were people who were saying, we're working really hard. But there was also, because it was a very large collaboration, there were a lot of people saying, well, we joined this collaboration and we've been sitting here waiting for this time. We want our turn with the data before we make it the public. And somehow, even though the rules were the data should be released earlier, it got delayed. It was released eventually, and you can actually find the data, a map with the dipole in it. It's not so easy to go through, but there are still sets of people on Planck who didn't want to release their part of the pipeline code, particularly in the Sanyov-Zeldovich effect crowd, which I criticized, but I just got in trouble for it, whatever. And so the answer is, the publicly funded stuff does usually have some kind of time deadline, and there's a tension between the members of the team who are working and doing hard and should get some rewards, and the people and the members of the team who think they were grandfathered in, and they want to hold that data for a while longer so they can get some more papers out of it. And there are still some people getting the data out of the Planck stuff, even though nominally it's been publicly released. And there's a big explanatory subject. There's just some pieces of the pipelines are not, most of the main pipelines are there, but some of the smaller other kind of activities, those pipelines haven't been released fully because people are thinking, well, I'll maybe do one more paper. So it is a tension. And the problem is, this is a problem which is known as the volunteer problem, in game theory and so forth, which is the example that's usually given is you live in a neighborhood and the power goes out in the neighborhood, but nobody from the power company happens to be around because it's way over in another part of town. And it costs you money to or effort to call up the power company and say, hey, you got to come fix this. And sometimes they charge you for it. Who's going to volunteer to call when there's a lot of people can be free riders and just wait for somebody else to call and do it? And that's a game theory, and in nature has solved this problem and a number of different things. You have an instability. There are some people who are going to be free riders, some fraction that are going to be free riders, and some people who are going to volunteer and do the right thing. And so it's a difficult problem, just like in many other things in modern society. It's a difficult problem to make this work really coherently. There is a significant effort to try and keep publications open, and there are even in Ireland, the university actually has an open publication for astrophysics, but it doesn't include all the background information. It includes the publications, it includes the data, but it doesn't include all the explanatory supplements and all this other kind of stuff. And it's a very valuable thing for the community to have, because it's very clear that the rate at which scientific progress occurs has to do with just how open the data are available. But it's a trade-off between the benefits of the individuals in the short term and the benefits to everyone in the long term.
Absolutely. Yeah.
Well, thanks for your insights. I like your comment you just made that there is a relation between the openness of the data and the rate of progress in science. Of course, that's the public aspect. And then you explain that there's a tension with the individuals, right, which is also understandable.
This is actually becoming much more relevant because, and I've just recently given a talk about how space is getting privatized. Research is starting to be privatized. We don't notice it so much in astronomy, but in some areas, in biological sciences and agricultural sciences and so on, a lot of research is being privatized. And there you have a real issue about openness and not openness, and about whether people are actually publishing all true, full results.
Yeah, although I think in our case, we have to focus on the things that we are familiar with, which would be, right, the physics and astronomy, cosmology, data. So we have a similar, as you know, issue in, say, LIGO, Virgo, and Tahra. And it's also one reason I asked, because it's even difficult to address this issue. It's not a very welcome topic from the insider's perspective.
Well, as George said, it is not always easy for experimental collaborations to publish their data. I'm a part of an experimental collaboration myself. And the truth is that you have to process your data quite a lot before, if it is of any use to somebody who is not in the collaboration. You can't just publish your raw data. It would make no sense to anybody. But I think we all know what we are talking about here. And that was the example that Stephen gave of, where can he get CMB data before the dipole has been subtracted out? I mean, that's actually at a pretty high level of processing. And we are simply saying that at that level, we would like to have access to data before it has been already interpreted in some framework, because one might want to question that framework subsequently. That's a very simple point. And I think that can actually be done subject to all the caveats that George mentioned, which are all good points and well taken. And as you say, in physics and astronomy, We don't perhaps have the kind of commercial pressures that are that come in medicine and biology and all the rest of it. So we could try to aim for open science. And apart from this Open Journal of Astrophysics, which he mentioned, there is also this journal now called SciPost. I happen to be an editor. We not only have it free for both authors and for subscribers, but all the exchanges between the referee and the authors is put up on the web page of the paper. So everyone can see what an author is going through when they try to publish something. And some people don't like that, but I think on the whole, it is of great benefit because we have this selection process in science that only the successes are recorded, not the failures, not the mistakes, not the questions asked. We are now doing it in this discussion panel, but this is not going to get published. Whereas for any paper, I think it is very useful to have the criticism of the knowledgeable referees actually recorded in public. The referee can choose to stay anonymous, but the criticism is important. And people learn a lot from such things. And yet, this is something that no journal has ever done before. We are doing it for the first time in the last couple of years. So I think there is still some things one can do towards open science, respecting those constraints that were discussed. It's quite possible. It just needs the will to, want to share science with everybody who is interested.